Okay, and welcome everybody. The audience is coming in and we are now live. Welcome to the third of the Generative Adversarial Collaborations kickoff workshops for CCN 2020. My name is Megan Peters and my co-host here is Ralph Hefner. And today we are talking about probabilistic perception. But first, before we do that, we wanted to do a quick intro of who the program committee is for CCN this year. So the chair is Nico Krieges-Korte, the co-chair is Gunnar Blom, then there's me and Ralph, and then there's Gemma, Eric, and Jennifer. And so together we've put together, instead of a traditional program this year, we've put together the Generative Adversarial Collaboration Project. And so you are in one of the kickoff meetings today. So we wanted to give a little context. If you've seen the last two GAC workshops, sorry that this is a repeat, but just to bring everybody up to speed. Basically, the idea behind the generative adversarial collaboration workshops is that science really benefits from alternative ideas and theories. And the problem is that a lot of times this kind of proceeds in parallel. So I try to prove my theory right, and you try to prove your theory right. And then we both publish, and then we, get into continued arguments after we publish. But the idea behind an adversarial collaboration and what we are calling a generative adversarial collaboration is that we kind of flip this thing sideways. So basically, instead of working on stuff in parallel, researchers with alternative theories will collaborate to resolve our differences, that they will together ideally design the best possible or fair way to disambiguate the theories, either through theoretical work or through empirical work. And hopefully science will actually really benefit from this. Healthy, friendly, and collaborative competition will really accelerate scientific progress. So this is the goals that we had in mind as we were designing this project. There's also a lot of benefits for the community and for you guys. So we all get to participate in these fun, open public debates. This is especially fun for early career researchers who get to see people kind of face off and think on their feet, which is always much more exciting. We also get to engage with you, the community. And so this means that this isn't a unidirectional kind of propagation of information, but that you all here in the audience and throughout the rest of the GAC project will be able to participate in the conversation. You can ask questions today, you can ask questions in the chat today, or in the Q&A box. And also, this is just the kickoff meeting, so the idea here is that you will continue to be engaged over the course of the GAC project this coming year. This will increase, of course, the diversity and number of ideas that we are putting together in the target area. And science also should really ask the important questions, not the trivial ones. So with the GAC project, we're hoping to provide a democratic platform to decide what's important. And so this is what was part of the open review process, that you all engaged with the GAC proposals this year. You identified their strengths and their weaknesses, and you also kind of communicated to us and to the organizers which ones you thought were important, or what aspects of each proposal you thought were important. And so this way we can find the questions that a lot of people really want to know the answers to. And finally, again, through open review, this is a very transparent process. So we've got this kickoff meeting today, then there will be position papers and options for community engagement and response commentary pieces to those position papers later on. And so this really facilitates a back and forth collaborative atmosphere between the folks who are giving the workshop today and also you guys out there in the audience. So this is the lineup for the GAC kickoff workshops this year. We've already had the competing theories of probabilistic computations in the brain, and is it that simple, the use of linear models. So today we're doing is perception probabilistic. And then there's a few others coming up as well tomorrow and on Friday. And really the goal here, and this is the last thing that I'm going to say today, is that we want to hear from you. The point here is not to have a passive audience that is being talked at for 3 hours, but to have a lot of community engagement. So please use the Q&A box at the bottom of your screen. Use the chat window. Make sure you set it to all panelists and attendees. And in the Q&A box, you can also respond to each other in comment threading. And keep in mind that even if a question gets answered and it's moved to the answer tab in your Q&A box, you can still respond in a thread. So there are lots of ways to get involved, and we'll also potentially be handing microphones to audience members or even pulling people up onto the stage as appropriate to engage in the conversation. So without any further ado, I will hand off the microphone to our GAC organizers for this workshop, and we will talk about is perception probabilistic. And I'm going to turn off my screen share, and I will then hand the microphone off to Dobie.
Wonderful. Thank you, Megan. Thank you for the introduction. Thank you for organizing this, to you and to the rest of the organizing committee. This is a wonderful opportunity, and I think we have already enjoyed tremendously the collaboration so far. And I can't emphasize this enough. We really want the input of the community. This is a very tricky, difficult question. We're actually going to start with the definition of the question. What are we even talking about exactly? And we really want to hear from you. We do not have the answers. We want to find the answers in a collaborative way. So let me share my screen here. Okay, everybody can see it? Perfect. So the question is perception probabilistic? All right. So let me first introduce the team. So we have 2 members for probabilistic perception, team 4. And this is Janneke Jehe. She's an associate professor at the Donders Institute. She works on computational models, fMRI, and behavior. We also have Rachel Dennison. She's an assistant professor at Boston University. She also works on computational models, behavior, neuroimaging, and there was a question of like, why are these flipped for Janneke and for Rachel? And there's no good answer to that. Then we have team against probabilistic perception, and this is represented by Ned Block, who is a professor at NYU, and he's a professor in the philosophy department, and he has done a ton of work in perception and consciousness. So he's going to provide the more theoretical perspective. And myself, W. Rachnev, I also work on computation, behavior, fMRI, and I'm an assistant professor at Georgia Tech. So this is the team, and this is the overview of the workshop. So we're gonna have really 3 parts. We're first gonna talk about the controversy. What is the definition of probabilistic perception? What are we actually talking about? We have realized that this is not actually a trivial issue, just defining what exactly is the object of disagreement. Afterwards, we're gonna give presentations on our arguments for and against probabilistic perception. Team 4 is going to go first, team against is going to go second. And finally, we'll discuss experimental ideas about how to move forward. For each of these, as you can see, there's plenty of time for audience discussion, and we really mean it. We want to hear from you. What are your ideas? Where do you think all 4 of us are wrong in our definitions? Or where do you think, what would be good evidence for, or what would be good evidence against probabilistic perception? So the goals of the workshop, so clearly we want to define the terms. So those 3 parts: define the terms, show the relevant arguments, and try to chart the way forward. This is in a way our main goal, but we have some other additional goals. We want to introduce the topic to non-specialists. So this is a topic where a lot of people have written papers that are not necessarily easy to read for beginners. And we want to keep things as simple as possible here. And we're not going to have almost any formulas or things like that. So we want to make it easy to understand, even if you haven't done work in this area. We want to engage in lots of discussion, and we also want to engage in lots of respectful discussion. I think that should be easier because all four of us really like and respect each other, and I think we respect everybody in the audience. But we want to really make this collaborative rather than aggressive or anything like that. Finally, we really want to encourage the engagement of women, underrepresented minorities, and trainees. This is, again, a field that happens to be dominated by white people and men, and I think more diversity within the field would be great, and we want to encourage that by, for example, we would like to start each Q&A by answering a question from a person from this group. If you want to self-identify when you're posting a question, feel free. If you don't want that, that's also fine. We'll try to pick questions having that in mind. Okay, so with that in mind, let's start with part one, which is defining the controversy. So what are we talking about? A quick introduction on just the basic terms. So what is, first of all, let's start with the very simple stuff. What is probability in the first place? The probability of an event is really a number between 0 and 1, where 0 indicates that something is not possible, and 1 indicates that something is certainly going to happen. So let's give a few examples. So this comes from a textbook that is in preparation by Mark Hording and Goldreich. And for example, let's talk about, you look at the sky and you think, is it going to rain? So you can think of, with some probability, the answer is yes. With some probability, the answer is no. And according to the authors, this seems to be more likely rain. I don't know what they're talking about. When I look at this, I don't think it's likely to rain, but that's part of the issue of probabilities. You can think of slightly more complex situations where you have some symptoms, and there can be several possible explanations for these symptoms. And you can also think of continuous situations where you look at, for example, a car in front of you. What is the distance to that car? Now, you don't have discrete events or discrete potential causes, but you have a continuous space. Now, one thing to mention is, for these to be actually probabilities, here they're just bars that have some height. They need to add up to 1. So the probabilities of all of the possible events should add up to 1. Or in the case of a continuous distribution, the area under the curve should be 1. So a few relevant concepts that are going to come up. We're going to talk about likelihood functions. We're going to talk about prior distributions, and we're going to talk about posterior distributions. These are not going to be central to what we talk about, but these are terms that are just going to come up once in a while. And oftentimes they would come without the second word. So we just talk about the likelihood, about the prior, about the posterior, with the second word here being implied. So let me come back to this in a second. The other term that is probably even less familiar that we're going to talk about is generative model. And a generative model is really not complicated. It's the description of of the world and how it generates internal observations. So for example, if you are looking at me, like at my video, you have some description of, there's people out there, they can be male or female or transgender, and they can talk and things like that. So you have some high-level description of the world, and then you know how this world generates observations that you actually take in. Now, this is again from an article from Wei Jima in Neuron on primer on Bayesian computations. And he gives this simple diagram. So we start with an observation. So you have some sort of a percept, some sort of a raw percept. Then that generates a likelihood function. So for what actually generated your percept out there in the world. You also have a prior distribution of what is out there in the world. Based on this, you can combine them using Bayes' theorem into a posterior distribution. And then you can also combine with a cost function to to produce the best action or response. We're not going to really talk about cost functions and actions. We'll mostly talk about the likelihood function. And the question is the likelihood function, is it simple or is it complex? And I'll come back to that in a second. And I hope this helps a little bit, but let me just go straight into the relevant part here, which is how do we actually define probabilistic perception? Okay, so if you take a second and actually answer this for yourself, I think that would be useful, because you probably realize that there's no clear, simple answer. And I think most articles that talk about this, they don't necessarily give, a definition that is like, here's probabilistic perception in a sentence. So somewhat informally, we're going to define probabilistic perception as the idea that individual percepts represent probabilistically. So this is a very general definition. And I want to mention that the question here is not really about whether perception is Bayesian or not. This is going to come up a lot, and I think that the groups for and against tend to be also groups that, strongly believe in Bayesian representations in the brain versus don't believe. But it's really a separate question. So one can have different internal representations that are either probabilistic or non-probabilistic, independent of what they believe about where the brain is Bayesian. Okay, so there's two critical features here that are very important. The probabilistic representation should be available for decision making rather than implicitly baked in. We're going to talk about this in several different ways. We're going to talk about the output of perception, for example. That's one phrase we're going to use. Or we're going to say things like the representation should be available for flexible and deliberate computations. And in all of these cases, we mean that you should be able to do decision making on it. It shouldn't be just implicit somewhere in the system where you can't have any access to it. The other component is probability should come from perception, not from cognition. So we're not discussing here cognitive probability distributions. We're discussing perceptual probability distributions. So let me give you an example that would make this a little bit more concrete. If you're in the US, you probably know of the game of baseball. If you're not in the US, you may not know too much of this game. Basically, if you're batter, a pitcher is going to throw at you, and they need to hit the strike zone. And if they do, then you need to hit the ball. It's not a super complicated game. So within this game, we can define the perceptual representation and the cognitive representation. So let's talk about the perceptual representation. The perceptual representation is going to be, how do you represent a single pitch, right? A single throw of the ball. And you can think of two possibilities of the immediately. One is no uncertainty. The ball is landing there. This is the entirety of my representation. I don't know anything else. I don't have any representation of uncertainty. And the other one is I have some sort of a full probability distribution over landing locations where this is the most likely location, but there's all kinds of other possible locations. Now, this is on a single pitch, and this is perceptual representation. Now, you can also think about cognitive representation, and this can come in several different varieties, but one obvious one would be the prior knowledge of pitch locations. So for example, you may think this pitcher throws to the right, or maybe he's likely to throw to the right on this particular pitch. And importantly, this is not what we're talking about. And this kind of representation, you can actually assemble this. So you can have a probabilistic representation in cognition that can be assembled completely from non-probabilistic perception. So let's say you don't have any representation of uncertainty. You only get a point estimate like that on every throw, but you observe like 15, 20 throws. And from here, you can assemble a probability distribution. So this is what we're going to talk about: perceptual representation. What happens on a single pitch? This is not what we're going to talk about. So whether or not the brain does probability distributions over trials, that's also interesting, but that's not the topic here. That sounds good. All right. So a couple more things to say here. So the definition that we're using, the output of perception for a single stimulus on a single trial, right? This is what we are interested in. And a couple of caveats: the output of perception doesn't necessarily have to be conscious. So we actually, all four of us, agree that conscious perception is not probabilistic in the sense that we're talking about. But the output of perception doesn't, may be probabilistic without consciousness being probabilistic. And we also want to say, if you're interested in a different type of question, whether the representation of multiple stimuli over multiple trials are probabilistic or not, this is also interesting, and it's just not the topic of the discussion here. We're interested about what happens on a single trial of a single stimulus. Okay, so if you followed so far, you'd probably see that there's this standard dichotomy in the way we talk about it. Perception either probabilistic or non-probabilistic, and that's fine. But the way we talk about the probabilistic and non-probabilistic is a little bit constrained. So this is this is a standard way in which this is represented. So the red here is the likelihood function of a landing location of a tennis ball. The green is the prior, and then the yellow is the posterior. You combine the two, and so the likelihood is this whole probability distribution, and this is probabilistic perception, and then non-probabilistic perception is a point estimate, and that's fine. So this is probabilistic perception, and this is indeed non-probabilistic perception. But it's important to say that in this standard dichotomy, there's only two options, where it's either a single point estimate or it's a full probability distribution. And this is actually a little misleading. It's not that there's only two options actually in reality. We think that one can identify at least 4 different schemes that are going to span the space between option 1 and option 2, where an option 1 and option 2 are actually the extremes. So let's talk about these. So the example that we're going to work with is a bar that is moving in a particular direction. And then we're going to look at the underlying sensory activity. You can think of this as in being in V1 or some other brain area. And what you're going to observe is different neurons tuned to different orientations, have different level of activity. And when you record from all of these neurons together, you get some sort of a population code, right? So this is the activity that you observe. Now, the important thing is one may or may not have access to all of this activity for downstream computations. So the question is, what do you actually have access to? And here's where the 4 schemes come. So the scheme 1 is the same as what we've been talking about. It's a single point estimate, and it says that the information available for downstream computations is just a single point. You think it's like 60 degrees, and that's the entirety of what you have. You don't know if you're certain, uncertain about it. It's just 60 degrees, that's it. Now there's a second possibility, which we call point estimate, and it's a long title, plus activity strength that cannot be converted into probabilities. So the way we explicitly defining this is there is some sort of a information about uncertainty, but you cannot, either that information is not in a form that can be converted into probabilities, or the brain, even if that information could be, the brain just doesn't know how to convert it into probabilities. So one example is just the point estimate and maybe the firing rate of the highest neuron, but it could be any kind of transformation of this distribution. The point is, this is the representation, and the brain does not know how to convert into probabilities, making this by definition a non-probabilistic representation. Now, a very similar representation can be virtually the same thing, 2 numbers, the point estimate plus variance, but with the caveat that now the second number is such that the brain knows how to convert this into probability. So I'm representing the variance or standard deviation here on the x-axis, And if you have the mean and a standard deviation, and for example, you assume a Gaussian distribution, then you know how to get every point on the distribution. So you have the mean, you have the variance, and importantly, you know the formula, right? You know how to convert these two numbers into the probability distribution. So that's scheme 3. And finally, scheme 4 is you have explicitly a full probability distribution. So this can be some transformation of this. And importantly, now you have moved from activity into probability. So you can extract, so this sums up to 1. So you can extract the exact probability of the different orientations. And it's not just a point estimate with some sort of one additional number. It is a whole distribution. Okay, so here's the same 4 schemes. And let's quickly talk about what models assume which scheme. For scheme 1, there's some, I don't even know how many people know about these threshold models. These are models that used to be very popular maybe 50 years ago or more. They're almost non-existent anymore. And you can think of constrained versions of the derivative diffusion model where you just hit the boundary and that's the entirety of what you get as being scheme 1. So pretty much nobody believes in that, but I'll get back to that. Scheme 2, you can say the standard string detection theory is a scheme 2 kind of a theory, as well as race models where you hit one boundary and then you can look at the level of activity in the other accumulator, and that difference can be your second quantity, the activity strength. And most convolutional neural networks, if you look at their last layer, that seems to be the closest to scheme 2. So there's some activity level there that you can use maybe to judge uncertainty, but it's not a probabilistic representation. You can't immediately extract probabilities from there. Scheme 3, we don't think there's any theories that are specifically scheme 3. So maybe there are, if so, we don't know about them. And scheme 4, there's a number of theories, and they were nicely presented in the first GAC, probabilistic population codes, distributed distributional codes, neurosampling. And I need to make the clarification for neurosampling, especially if you get one sample, well, you're in scheme 1. And if you get 3 samples, maybe that's not really scheme 4. But if you get 15, 20 samples, then it's scheme 4. So there's a caveat that for neurosampling, timing is important. And to some extent for the other ones, if you have really low firing rate, if you only get 3 action potentials, that's probably not a probability distribution. Okay, so let's make some distinctions here. We can draw a boundary between scheme 1 and the rest, and we can say this is the distinction between uncertainty not being represented versus uncertainty being represented, right? So that's great. We can draw this distinction here between the first 2 and the last 2, and this will be the distinction between non-probabilistic representation versus probabilistic representation. Okay, and finally we can draw a distinction here, and that would be the distinction between some sort of a summary representation, 1 number here and 2 numbers for scheme 2 and 3, versus explicit distribution, which can be a lot more complex than 2 numbers. Okay, so very quickly, there's a lot of suggestive evidence already against scheme 1. So it comes from Q combination studies, for example, and I'm not going to go into any detail, but this is studies where you combine the information from, for example, 2 modalities like vision and haptic and touch. And we know that there's many findings of near optimality in that, and that is difficult to observe if you don't have any representation of uncertainty. So if you only have a point estimate for each of them, you wouldn't know how to combine it. And there's caveats for all this, but I'll mention that in a second. The other one is confidence. So we know that people can use confidence to predict their accuracy. And again, if you only have a single point estimate, that is difficult to do. Finally, neuroevidence. There's a number of studies that show that uncertainty can be read out from the sensory cortex, and that uncertainty correlates with behavior. Some of this research has been done by Janneke, and she's going to talk about it a little later. And again, this would be surprising if all you get out of the sensory cortex is a single point estimate, because so in all of these things, it is not impossible that some sort of different thing, like my attentional state or my decision time, is used as a proxy for uncertainty and not the perceptual representation itself. But that would be very surprising, and there's evidence from many different directions that argue against it. So overall, none of us supports scheme 1, and we're not aware of anybody in the field who supports scheme 1. But for the remaining ones, there's really question marks. It is not clear what is what is the best scheme out of the rest. And quickly about the way forward. So this boundary, the first boundary, well, that's already established. So we're not interested to talk about it, to talk about this boundary. That's done. This boundary is going to be very difficult because scheme 2 and scheme 3 are so similar. They both have two numbers, and you can say, well, this is more optimal and this more suboptimal. But if you see one example of optimality, this can explain it. If you see one example of suboptimality, scheme 3 can explain it. It's a tricky question. But this one, the distinction between scheme 4 and the rest, this seems to be the most feasible. And that's why we're going to focus, especially in part 3, we're going to focus mostly on this distinction here. A lot of our presentation is also going to touch on this distinction, but really the experiments that we have in mind, or at least the experimental approaches that we have in mind, are going to be here. So the empirical question that we set out in our GAC, and I just want to repeat it here, is can humans, and it's a mouthful, can humans perform flexible and deliberate computations? So the idea is we're talking about the output of perception that can be used for decision making. So that's where the flexible and deliberate computations come in, that require access to more than summary statistics. So is there evidence that we need more than mean and variance, or that we represent more than mean and variance of a perceptual likelihood function or posterior on a single trial basis? So that's my presentation. I hope we have clarified our position about where really the question is and why it is not necessarily obvious already what the answer is. All right, so let me open it up for Q&A.
Great, thank you, Dobie. And I'm just going to jump in here and end this poll, which we launched towards the beginning of Dobie's presentation. The results are pretty definitive here, that most of our audience, I think you all can see this right now, most of our audience says that yes, perception is probabilistic. Although I did see in the chat as Dobie was talking, there were a couple people who said, based on this definition, I would now change my vote. I don't know how they voted to begin with, but we'll see. So you'll have a chance to re-up your answer at a couple points throughout the presentations here. So I'm going to go ahead and turn off this poll. And then we will go ahead and move into the Q&A period. And we've got some great questions, both here in the Q&A, and there were a couple that came in the chat. So I just want to say really quick, please, if you don't want your questions to get buried in the chat, if it's kind of a stream of consciousness thing, great. But if you want them to actually get addressed, it's better to put them in the Q&A box. Otherwise, they will just disappear as we scroll through the chat. So a couple questions here. And I guess, Dobie, these are for all of the panelists, or do you want this to be for you only?
Oh no, all the panelists for sure. Yeah.
Okay, great. So we have a first upvoted question here from Andrei Chechverikov. And the question is, how do you define a single stimulus and a single trial? And why do you add these limitations? Each image has many pixels. What's the difference then between showing one Gabor and several? What's the difference between showing one stimulus for 5 seconds and 5 trials with a 1 second stimuli? And Andre, we're also going to hand you a microphone if you want to follow up on this too. So anybody want to take this?
Jump in, I can maybe address this. So the reason is we want to really distinguish between perception and cognition, right? So if you have a high-end trials, as I was showing earlier with the example here, well, your perception can be non-probabilistic, but your cognition can be probabilistic. And if you're interested in perception, then it should really be a single percept. And in the language of experiments, that means a single stimulus on a single trial. Yeah.
Can I add to that? Can you hear me? Yeah. Can everyone hear me? So in my mind, these probability distributions, they really reflect, or they say something about the amount of information that's available. And the amount of information concerns the amount of information on a single trial, or the amount of information about a given stimulus. So that's why probability distributions or likelihoods are really computed for a single trial, or information is something that's computed about on a single trial. And that's what we're really talking about, I think.
And can you, sorry, can you also clarify why are you talking about a single stimulus and how you define it?
Toby?
Yeah, well, that's a good question. I don't have a great answer, honestly. I think that it's the kind of thing that is somewhat intuitive, that if you have a single object, that becomes a single stimulus, versus if you have multiple separate objects, they are multiple stimuli. But I take your point that every stimulus is multiple pixels. Now, the question is, how does the visual system deal with this? So we know that, for example, a face, there's eyes and mouth and all of that, but it's also just a face. There's a holistic representation, and in a way, we're interested in the holistic representation. There's debate for sure, and I would personally rather err on the side of being too conservative here than too liberal, in the sense that we really want to stay within perception. We don't want to get into situations where you can answer or you can do the task using cognition.
I also don't really see what adding multiple stimuli would add, because the probability distribution is over a stimulus, right? So then you would have multiple stimuli and combine the stimuli maybe, and then that could be something that we could do, and we could discuss that later about like experimental paradigms. But effectively, it's a probability distribution over one source or one interpretation. So that's why it's one stimulus, at least the way we think about it right now, in terms of our definitions, or in terms of like how we're going to test this. And yeah.
Great. Thanks. Okay. And Andre, thanks for jumping in there. So we'll go ahead and move on then. And just so that you guys are all aware, these questions will be marked done and move into the answered column in your Q&A box, but you can still engage with them there. And so they don't go away, they just move to a different tab. So please feel free to continue engaging. Okay, so the next most upvoted question is from Peter Koch. And the question is, would Friston-style predictive coding be an example of scheme 3, where separate neuronal populations encode the mean and the precision? So you have maybe separate populations that are encoding each of these two things. So I'm going to go ahead and hand Peter a microphone. And why don't we go ahead and answer this question? Anybody? Is predictive coding scheme 3?
Great question. I think that's for Carol maybe to answer. So there's also a question of, you know, is there really a probabilistic representation? Can you convert it into probabilities for other world states, or can you not? So if you can't, it actually even becomes scheme 2. If you can, it becomes scheme 3. And maybe in some versions of that, you can actually do even more than that. In that case, it becomes scheme 4. But yeah, I don't have a great answer. I think that there's different versions of this model that, as far as I'm aware, and it's hard to pin them to one of these schemes. But Peter, maybe you have. Do you think it's scheme 3? I know you work more with that model.
Well, I don't really have an answer. That's why I was asking you guys. But it did strike me when you described the 4 different schemes, and I think you mentioned there wasn't really you didn't really have a good example of a scheme 3. This seemed to me a potential one where separate populations of neurons are meant to encode what the best guess is of what's out there, and then other populations, the precision of that, so the inverse variance. That seems like a 2-parameter type of representation to me. So it's just, yeah, wondering what you guys think. Maybe Janneke, do you have a view on this? I know you've worked on some predictive coding models as well.
Oh, but that's a long time ago, and I've never actually really thought about that real deeply.
Okay.
In terms of this. So no.
Okay.
Yeah, I mean, I think Peter, I take your point. I think it fits probably best in scheme 3, and I think that's a good thing for us to think about, whether we can add that there. I think it would be good to have an example there.
Great.
Okay, thanks.
Okay. Thanks, Peter. Okay, so let's move on then to the next question. This is fun. We've got a question from Weiji Ma. It seems that perception versus cognition distinction gets mixed up with no prior versus prior. A prior over orientations could be very low level and automatic or non-cognitive. I'm okay with leaving priors out, but then let's leave all priors out. And Weiji, we've handed you a microphone as well, so you can go back and forth on this.
Hi everyone.
Hi.
I have nothing to add to the question.
I'm happy to jump in here. I think that you're right. We don't want to confuse perception versus cognition with prior versus no prior. This is really more of an experimental design consideration. We want to make sure that when we test this question, there's no alternative explanation for the results where there could be some prior information that's been learned by cognition that then people use to do the task. So I think that's right, that there can be very low level perceptual priors like over orientations, and we're going to talk a bit more about those later on in the workshop. We just want to avoid the possibility that people have explicitly learned some prior distribution in cognition and then use that to perform the task. That's why we've tended to focus on likelihoods here. But if there are ways to use a prior that we can ensure is not also learned in cognition, I think that would be totally fine for our purposes.
Yeah, I agree.
Great. Well, that was easy. Okay. Thanks, Weiji. Let's move on then. So the next question is from Christoph Basinski, and I'm sorry if I mispronounced your name. The question is, can you have multiple single point estimates with self-estimated precision does this count as probabilistic perception? And Christoph, we will go ahead and hand you a microphone, and then we can have one of the panelists take this question.
Yes, thank you. This is, I guess that it's a similar question to the one before about Friston style predictive coding. This is what I had in mind. So I guess you kind of answered that already, but I was wondering if you could even think about single point, like multiple single point estimates.
So at that point, they're not point estimates anymore. They're just samples of some sort, right? That you assemble together.
Well, you can think of it like, I don't know, maybe like bimodal distributions, things of that sort, like two competing estimates that you kind of need to
yeah, so I think in our definition, that would be a probability distribution. So the way we think about point estimate is you take the mean of the distribution, maybe the mean of the two modes, or just one of the modes, you pick one of them, and that's what you represent. But if you're representing both of the modes, then you're already in scheme 4, even if it's a simple representation of the two modes.
All right, thank you. Peter Koch, I guess, and Rajesh Rao had just commented on this as well. So it's scheme 4, I believe, in your kind of
yes,
topology,
exactly.
right?
Mm-hmm.
Okay, thank you.
Great, thanks. Okay, so we will move on. Oh, well, if we just go down in upvote fashion, then we'll bring Weiji back. And Weiji's question again is, Dobie, you also use the word explicit about representation of the full probability distribution. This is a dangerous word. Even those of us who see evidence for the full distribution don't think that you can immediately see them in a neural recording. The distribution would still have to be decoded, be implicit. Back in 2002, even Peter Dayan didn't manage to distinguish explicit from implicit. So it's safer to avoid that terminology unless you are prepared for a long, difficult, and tangential discussion. Is this a question, Weiji?
Yeah, let me just say, I'm not prepared for that. And, you know, terminology is something that we're still trying to find the best terminology. So by explicit, what I really want to mean is available for decision making, right? Nothing more than that.
Okay, that helps. Yeah.
I think another thing to say about this is that the kind of implicit that we're worried about is what's baked into the architecture of the system. And so not freely available for a wide variety of tasks. So it's really the deep implicit that we're concerned with.
So that's actually a different distinction, right? So you could think that some information is stored in activity patterns and some in synaptic weights. And most of us are thinking about the transitory variation in the activity patterns as representing this probabilistic information, right? So that would then be sort of less baked in, if you want. I don't know exactly what your definition of baked in is. It's sort of half baked in, but then I would still call both of those implicit. But again, if your only goal is to say that it's available for decision making, then I don't think you need the word explicit at all. You can just say what you just said. Yeah.
It isn't just available for decision making, it's available for a wide variety of processes.
Okay.
Great, thanks, Weiji. Okay, so we've got time in this block for a few more questions here, so this is great. The next question is from Heiko Herbert Schwitt. And the question is, where in this list would you put representations which include more or other summary statistics than estimate and uncertainty? Even summary statistics which are not in any way optimized to represent probability will at some point allow very close approximation of the probability distribution, which might shift this towards scheme 3 or even 4. And so Heiko, we've given you a microphone to follow up on this as well. Panelists?
Yeah, hi.
Hi, Heiko. Thanks. So as you say, if you have a lot of summary statistics, you can approximate a full probability distribution. And I think we're prepared to put that under scheme 4. So we are drawing a very minimal definition of scheme 4. The most minimal definition we could draw is having more than 2 summary statistics available for downstream computations, so more than mean and variance.
Yeah, so I think a bit of clarification for the question would be like coming more from like a really neuronal implementation thing, right? Like I think it's not so much controversial that we will have some transformations of this. And my worry is essentially, even if I don't do any, like don't aim to do any kind of probabilistic representation, but just, you know, do some transformations of this and just keep enough information. You know, if I just keep enough information, it's still possible to, from that, construct a probability distribution about the stimulus. And I'm more worried that this might be classified as probabilistic computation, as you say, although it was, you know, never meant to, or like, you know, this part about you had for scheme 3 that the brain knows how to decode this seems to be very hard to check. And like you know, like that's the kind of direction where I'm coming from with this question. I don't.
Are you asking like how we would need some way to show that the information is being used in a probabilistic way?
Yeah, like this is the question, right? Like a situation where you have many summary statistics, so you could do probabilistic inference with this. You know, but it's not mean and uncertainty, so not something which seems very suitable for this, but you know, it's some strange sums over some strange orientations, more like a random feature kind of representation.
Yeah, I think it's a really important point, and we're going to have to think about this really carefully when we think about the experimental design. An important thing for us is that the representation can be used for decision making, and when we say can be used, we want to show that it could be used in a way that is consistent with probabilistic information being available to the decision process. So if it's just like a grab bag of numbers, we wouldn't expect that grab bag of numbers to be you know, combined in a way that's consistent with probabilistic inference, for example, or combined with other information, prior information, et cetera, in a way that's consistent with probabilistic inference. So we're going to have to do something experimentally to demonstrate that it's more than 2 numbers, but also that they're used in a probabilistic fashion. So that's something we'll have to think about really carefully.
Yeah, thanks very much. I think losing the strong connection to the like mean and uncertainty in this, I think, yeah, it helped make it clearer for me at least. So thanks.
Okay, great. Thanks for the question.
Great, thanks. And Christina Sevian has also pointed out in the Q&A that DDCs do exactly this. And so we'll mark this question as answered, but please, you know, continue to chat in the Q&A box. Let's do one more, and then we'll move on to the next section. And so the next most upvoted question is from Olenka Graham-Castaneda. And so the question is if perception is probabilistic, then the following motor response would be as well. So where do you see free will fitting in, if it fits in at all? And there's a follow-up from Sam Zhang saying, I don't think probability would give you free will. Freedom implies agency and control, and neither probabilistic nor deterministic mechanism would give you more agency and control. So shall we comment on this before moving on?
I just want to say I agree completely with Sam Zhang's answer.
Okay. Any other comments though on the main question?
Well, the comment is that probability has nothing to do with free will. Free will is not a matter of your responses being random to some extent. It's a matter of agency and control, and that's compatible with full determinism and no probability.
Anybody else? Okay, great. Well, thanks, guys. Do we want to move on with any of the other questions in particular, or would we like to move on to the next section? What do you guys think?
Should we take just a short break before the next section?
Sure, we can take a break. So if we didn't get to your question, that doesn't mean that we won't necessarily get to your question, or that the panelists won't. Why don't we take a short break? We'll be back here in 3 to 4 minutes, and then we'll continue. And we can have the panelists and everybody just mute your mic and turn off your camera, and we'll be back here in just a few minutes. Okay, see you guys then. Okay, and we are coming back. Let's go ahead and get set up for the next section. So next up is part 2. It looks like, Rachel, you're going first, right?
Yep, should I share my screen now?
Go ahead.
Okay.
Okay, and the polls that you want to run here, are those at the beginning, or shall we do the one at the end of the part 1 presentation now poll as you're getting started?
That sounds good. Yeah.
Okay, so I'm going to go ahead and launch this poll. For those of you in the audience, we're launching a poll now. This one has 2 questions, so please answer both of the questions. And we'll just leave this up as people come in to the room and filter back in. Great.
Okay, should I get started?
Yeah, why don't you go ahead and get started, and we'll leave this poll up if that's okay while you're going.
Yeah, that's great. So we have, as you can see, these series of polls, which we're going to ask everyone as the workshop goes on to see if what you think at the beginning, and if we manage to change your minds in one way or the other by the end. So that'll be an interesting feedback. So here we start out with part 2, the arguments for and against probabilistic perception. And I am going to kick it off with the case for yes, humans can flexibly use probabilistic perceptual representations. Okay, and I want to start out by motivating this, motivating why would we be interested in using probabilistic perceptual representations at all? Why does probability matter for perceptual decision-making? Perceptual decision-making must deal with uncertainty due to both noise and ambiguity, and probabilities provide a formal way to express this uncertainty. So let's look at some of these sources of noise. There are many sources of noise, which we can divide into external and internal noise sources. External noise corrupts the image that reaches the retina. So sources of external noise include distance, darkness, fog, etc. Internal noise is what we call neural variability that is unrelated to the stimulus. And all of these sources of noise contribute to an observer's uncertainty about what they are seeing. But even in the absence of noise, an observer will have uncertainty about what they are seeing due to ambiguity. So here's an example of ambiguity. What 3D shape is this in this image right here? So even though we can see this image perfectly, There are different ways of interpreting it. There are many 3D shapes that are consistent with this 2D image. And that's shown here. So these three curved surfaces have different curvatures and are viewed from different angles, shown here. But all of these different 3D scenes produce the same image on the retina. And in fact, there are an infinite number of combinations of curvatures and slants that are consistent with this image. These different combinations are shown in these dark regions on this plot here. And so notice that the likelihood function relating these two world variables to the image is complex and not Gaussian. A generative model captures the idea that different properties of the world interact to cause the retinal image. And a probabilistic representation handles the fundamental ambiguity in retinal images due to the fact that the same image features can be caused by different combinations of world variables. So this is the representation that an ideal observer would have. In addition to incorporating the image itself via the likelihood function here, an ideal observer making a perceptual inference would also incorporate prior knowledge of the statistical regularities in the environment. For example, the observer might know that they almost always look down on objects rather than up at them, and that objects are a little more likely to be convex, positive curvatures here, than concave. The likelihood in the prior can be combined to form the posterior probability distribution, which is shown here. So these dark regions then are consistent with both what we see from the likelihood function and what we know from the prior. And the spread of the dark regions expresses the ideal observer's uncertainty about both surface curvature and slant given the image. So this posterior probability distribution is also not Gaussian. So it can't be captured by just two summary statistics of mean and variance. So there's a great deal of work suggesting that something like probabilistic inference takes place within perception. And the question we're asking here is what information is then available to downstream computations? The four of us all agree that more than a point estimate is available. That's the rejection of scheme 1 that Dobie introduced in part 1. But how much more is the question. So first, let me state the team yes or team 4 position. So we hypothesize that complex or non-Gaussian probabilistic representations are available for perceptual decision making. That is to say that the summary statistics of mean and variance are not enough to characterize the information available for decision making, which implies flexible use of more than two numbers per world state. So for example, our position is that if this is the perceptual distribution, which you can see is a little bit skewed, then information about the skew of this distribution would be available to downstream computations. A few clarifications on the team yes position. First of all, the brain does not have to represent the correct probability distributions. Second, and relatedly, probabilistic is not the same as optimal, as Dobie already introduced in part 1. For example, you could do probabilistic computations with the wrong distributions and be suboptimal as a result, even though the information was probabilistic and the computations were probabilistic. So these two aren't equivalent. And third, it is clear that the brain has limited resources and so cannot represent probability distributions with infinite precision, as has already come up in the Q&A. For our purposes, it is sufficient if the brain approximates probability distributions with some number of statistics greater than 2. We have 4 arguments for the yes position, and I will describe each in turn. First, more than a point estimate is represented, and this information is reflected in behavior. Most of the evidence for this was already covered by Dobie in describing why we have all rejected scheme 1, and Janneke will discuss some of this work that her lab has done in detail next. So I will leave this argument now and go on to argument 2. So argument 2 is a normative argument. Complex probability distributions should be represented and passed on to downstream computations. And that is for multiple reasons. So first, more information generally leads to better performance. Second, inverting a generative model is a general solution for inference. And to do this effectively, probability distributions must be maintained. So in other words, to make good decisions, it's very useful to have a probabilistic representation. And third, combining multiple sources of information leads to improved results when probabilities are taken into account. And doing so requires this probabilistic transfer of information between brain areas. We already have reason to believe that this is done within perception. So here we're arguing that this should naturally follow into downstream decisions as well. Argument 3 is a plausibility argument. So complex probability distributions can be represented and appear to be reflected in behavior. There is work showing that neural activity can theoretically encode complex distributions. The first CCN GAC workshop had great examples of that and discussed that a lot. There's also behavior work that suggests that humans use complex priors, for example, when judging the orientation of a stimulus or the speed of motion. And this image on the right here is an example of how vertical and horizontal orientations are more common than oblique orientations in natural scenes, forming a complex non-Gaussian prior. So these behavioral studies provide evidence for the use of complex probability distributions at the level of perception. Which naturally leads to the question, argument number 4, if there are probabilistic representations for perception, why not for decision making? There is evidence for probabilistic computations in perception and also in the motor system. So why should probabilistic representations suddenly disappear when transferring information from the perceptual system to downstream decision making, only to reappear later? And indeed, why would we expect fundamentally different neural codes for perception versus cognition? Although there is a philosophical debate on how sharp the distinction between perception and cognition is, as far as I'm aware, no one suggests that different parts of the cortex are performing fundamentally different computations. So to summarize then, the arguments for yes, their perception is probabilistic according to the definitions that we've set out. First, more than a point estimate is represented and this information is reflected in behavior. Second, complex probability distributions should be represented and passed on to downstream computations. Third, complex probability distributions can be represented and appear to be reflected in behavior. And fourth, if there are complex probabilistic representations for perception, why not for decision making as well? And now I will turn it over to Janneke, who will discuss some of the best current empirical evidence for argument 1.
All right, so I am going to share my screen. I think you can see my screen right now. All right. So we all tend to think that our eyes are very reliable transmitters of information about the outside world. But in truth, the signals that they provide from moment to moment are noisy and incomplete. For instance, consider driving in your car and you're trying to estimate the distance to the car in front of you. Now, let's say you estimate the distance to be about, let's say 40 meters. But it could, of course, also be 30 meters or perhaps even 50 meters. In other words, our perception is actually consistent with a whole range of distances. And this range can also change, for example, when driving at night, when perception is consistent with a much wider range of possibilities. So we're typically much more uncertain of our estimates. But how do people make decisions on the basis of such limited and uncertain data? How do we do this? So one of the outstanding questions in this field of perceptual decision-making is how uncertainty is represented in cortex. And theories of neural coding propose that uncertainty is reflected in a probability distribution that's encoded by whole populations of neurons in cortex. And this theoretical work was, of course, covered by one of the other workshops. So in other words, these theories propose that when visual areas get activated by an image, neural population activity in these areas does not represent a single distance, but rather these areas represent a whole range of possibilities, where the width of this range reflects the degree of uncertainty. And this range can, of course, also change under different viewing conditions, for example, when driving at night. But the question is sensory information indeed encoded probabilistically? Is this the neural representation of uncertainty? So what we're going to do today is address two questions. One, can we measure the uncertainty associated with stimulus representations in cortex? Can we measure these probability distributions? And two, do human observers also rely on this uncertainty in their decisions? Do they use this probabilistic information in their decisions? And this work was carried out by Ruben van Bergen, who is now a postdoc at Columbia, but at the time he was a graduate student in my lab. First things first, can we measure these probability distributions? So the way we addressed this question was as follows. We had 18 human observers perform the following task while they were in the scanner. So they would be presented with an orientation. There was a brief interval, a response window in which they would report the orientation of the stimulus by rotating this bar at fixation. Now, let's focus on these behavioral responses for a little bit. If this is the actual orientation presented on that trial, then on trial 1, the estimate could be something like this. And on trial 2, it could be maybe something like this. And on trial 3, it was this. So over trials then, this is a range or distribution of values with a width, so variability, and a mean. And these are two behavioral values that we'll focus on later on. All right, so while the observer was viewing all these orientations, we recorded their bold activity. And the question is, of course, what kind of information is represented in these patterns? So what we're going to do is see what kind of information we can decode from these activity patterns. And the way we approach that is as follows. Let's say we have these two voxels here in cortex, voxels that are indirectly measuring from neural populations in cortex. And what we can do is we can plot the response of one voxel against the response of another voxel. And that's shown up here for one trial, for a given orientation. Now this is for another trial for the exact same orientation, a third trial also for that same orientation, and so forth, a whole bunch of trials. So this is for orientation 1. We can, of course, also do that for another orientation, so orientation 2, shown up here. And of course, for many more orientations, even though they're not shown here. And looking at these responses, a few things are immediately apparent. First, voxel responses are variable, just because of noise in the MRI measurements, and potentially also because of noise in the neural populations underlying the voxel. And because these responses are variable, any given response is actually consistent with a whole range of orientations. And it becomes very clear when we look at the responses of these two voxels for a given independent test trial. Now, if the question is which of these two orientations was presented to the observer, then we're in a little bit of trouble, right? Because just from looking at these patterns, it could be either orientation. So in other words, there is some uncertainty about the presented orientation. But what we can do is we can estimate just how likely either orientation is given this particular test pattern, and that's what we're going to do. So this is for one orientation, this is the probability for the other orientation, and this is for all other orientations. So what we have then is a distribution of values, where this is the most likely orientation, and we can take the width of the distribution as a measure of the degree of uncertainty in our estimate. So what does that mean then? We have trial 1, there is another trial, and we can estimate these distributions or likelihoods. Now, trial 1 was perhaps a little bit less noisy, and trial 2 perhaps a little bit more noisy. And this is also reflected in the width of these distributions. So what we have then is a measure of trial by trial uncertainty. All right, so let's apply this to our data and see what we get. So in trial 1, we get this distribution, where this is the orientation estimate, and this is the degree of uncertainty in that estimate. So that's for trial 1. We can do that for another trial and so forth. And of course, these distributions, they vary in width due to varying levels of noise in the signal, as they should, right? Because there is noise in the measurements. But what we'd like to know then is, are these distributions meaningful? And the reason why I asked that question is because there are really two sources of noise. There's MRI noise and there's neural noise. And what we're interested in, of course, is neural noise. So the question is, do these distributions reflect something about the quality of the underlying cortical representation? So we reasoned that a more precise representation in cortex should result in more precise behavior, which is kind of intuitive. And what that means then is that if these distributions reflect uncertainty in the cortical representation, then decoded uncertainty should also be linked to behavior. So that's what we're going to test for now. And we did that in two different analyses. So for the first analysis, we relied on a well-established effect, which is that behavioral orientation judgments are more precise for cardinal than oblique orientation stimuli. And we also observed this effect in our own data, where behavioral variability was lower for cardinal than oblique orientation stimuli. So the question is, do we find smaller decoded uncertainties or more precise neural representations as assessed by the decoder for cardinal orientations? And interestingly, we do find narrower distributions, so greater certainty for cardinal relative to oblique orientation stimuli. And that is the first piece of evidence to suggest that the decoded probability distributions reflect the reliability of the underlying cortical representation. So that was pretty encouraging. But we wondered if we could push this even further by focusing on a single orientation. So we wondered, does behavioral variability also increase with decoded uncertainty, irrespective of orientation? So that's what we're going to test for now. All right, so what do we see? This is where decoded uncertainty was high. So the decoded distribution was, this is low, so the narrow ranges of the decoded distribution, where the dots represent single observers. And this is where the decoded distribution was high, so much wider distributions. And this is for in-between levels. And as you can see, the answer to her question is affirmative. There is a clear link between behavioral variability and decoded uncertainty. So this suggests that we can decode probability distributions that reflect the uncertainty in human cortex on a trial-by-trial basis. We can estimate the precision of a cortical representation on a single trial. And I should also point out that the stimulus properties here were held constant. So it's really internal variability that rendered these stimuli more or less certain. And that brings me to the second question of this talk. Do human observers also take this uncertainty represented in visual cortex into account when making decisions? Is this the representation of uncertainty that observers use in their decisions? And to address that question, we relied on another well-established behavioral finding that we also replicated here, which is that observers tend to report stimuli as being tilted away from the cardinal axes. For example, let's say the actual orientation was close to vertical, and the reported orientation deviated away from that vertical axis, again with a certain distribution as shown up here. So now we're talking about biases in the mean of this distribution. Just to give you a real-world example, these are the behavioral estimates of one of our observers with a clear bias away from the cardinal axes. So the underlying neural mechanisms of these repulsive biases are unclear. We simply do not know how they arise. But we do know that theories of these biases have a very straightforward prediction, which is that if uncertainty in visual cortex is used, then this bias should increase with uncertainty. So that's what we're going to test for now. So the question is, do we see larger behavioral biases with increasing uncertainty in cortex? So what do we see? This is where the cortical representation was fairly precise, where again the dots represent single observers. And this is where the decoded uncertainty was high, so much wider decoded distributions. And this is for in-between levels of uncertainty. So there clearly is a larger bias for greater decoded uncertainty. In other words, human observers appear to use some sort of knowledge of internal uncertainty in their perceptual decision-making. And we also recently found further evidence for this, as discussed in the paper cited below. All right, so what does that mean? We can use MRI to characterize the trial-by-trial uncertainty in perceptual representations. We have a metric for fluctuations in the internal representation. And observers also appear to rely on the precision of their internal evidence in perceptual decision-making. In other words, they appear to use probabilistic information in their decisions. And what does that mean then in the context of this collaboration? It appears that the fidelity of a cortical representation is represented in cortex and used in behavior. So more than a point estimate is used, and this is linked to the cortical representation of the stimulus. And we also know that these distributions decoded from visual activity can take a complex shape, as a postdoc in my lab, Andrei Chetverikov, recently demonstrated. But we do not know if all of the information contained in cortical activity is used. So for example, we do not know if such a complex shape is used in behavior. And this is of course one of the questions that the four of us are planning to address in this collaboration. So thank you, and thank you for your attention.
Great, thank you both. So we have now, it looks like Team Against is going to come up with a rebuttal to the evidence that has just been presented.
All right. Well, thank you, Team 4, for giving a very good argument for the wrong position. I will put a funny thing on me when I say things like that. Okay. All right. So, what are the counter arguments? What are the arguments for against? I will start with some theoretical arguments, and knowing that they had 4 arguments, I came up with 5. All right, so that's already evidence there. So one is, well, conscious perception is not probabilistic, right? We all agree on that. And this doesn't necessarily mean, of course, that the output of perception is not probabilistic, but I think it already puts the onus of proof on the team 4. So if conscious perception is not probabilistic, then the easiest, most obvious conclusion to make is that the output of perception is also not probabilistic. Another argument is that probabilistic perception is typically motivated by optimality. If you think about those 3 theories that we discussed under scheme 4, they're mostly motivated by optimality. But as Rachel may know, she has published a paper with me. Suboptimality is actually super prevalent. It's probably more prevalent than optimality. And well, if we have these schemes that really allow us to be optimal, then why is suboptimality so prevalent? Another argument comes from this idea of generative models. So in order to have probabilistic perception, you really need to know the generative model ahead of time. But there's an issue with that. So how do you learn the generative model? The issue is we almost never know the ground truth. In the lab, sure, you know the ground truth. You're shown many stimuli, you're given feedback. But in the real world, how many times did you see a bear? How many times did you see a lion for you to figure out the ground truth? How many times did you get any kind of percept and got feedback about it? And if you can't learn the true generative model, then how do you get a meaningful probabilistic distribution? I think you get a guess of some sort, and it's hard to assemble a probabilistic distribution. Number 4, probabilities are just difficult to compute. I mean, it's one thing to have some options for some things, for some world states, but it's a different thing to convert that into probability, numbers that add up to 1, and to compute with them. It requires a lot of machinery that the brain may or may not have. I mean, there's an argument that we have some theories that say this could possibly be done, but is it actually done in the brain? I mean, it requires a lot of stuff to be true for this to actually occur. And the final argument is people are actually really bad with probability. So we know that if you ask, there's many probabilistic questions that you can ask people, and there's so many ways to trick them. So if probabilities are so fundamental to perception, it would be surprising that then our cognition is so lousy with using probabilities. Again, these are theoretical arguments. I don't think they're going to convince anybody, but I think it also shows that there's a lot to think about if you do think that perception is probabilistic. Why are all of these things happening? So let me quickly go through the empirical evidence that I already covered in part 1 as evidence against scheme 1, and also argue that at least the first 2 of these are actually somewhat inconsistent with scheme 3 and 4. So Q combination, as I mentioned earlier, there's many findings of near optimality, so that's great, and that has been one of the explicit motivations behind scheme 4. So if you read papers that on probabilistic population codes and neurosampling, they oftentimes don't really motivate the probabilistic representation using empirical findings, but when they do, it's usually Q combination that is being used, and that's great because that is strong evidence against scheme 1. But again, if you only have 2 options, scheme 1 versus scheme 4, then that's evidence for scheme 4. If you have many options, then that's not evidence for scheme 4 anymore. And moreover, there's actually just as many findings of suboptimality in Q combination. I think people forget that. If you look at the literature, it's actually probably 50-50, if not more than 50-50 in terms of more people finding suboptimality. And if suboptimality is actually that common, and you have built something that is specifically to explain optimality, well, that's isn't that a problem for schemes 3 and 4? Why is suboptimality as common as it is if we have all of the machinery that would allow us to be optimal and then we are suboptimal still? So why did we build this machinery in the first place? So similar with confidence, right? So people can use confidence to predict accuracy, so that's great, and that's a problem for scheme 1. But there's also many findings of confidence accuracy dissociation. So these are conditions where you have two conditions that look very similar and they match on accuracy, but they differ in confidence. And if that's actually as common as it is, isn't that again a problem for scheme 4? If we have these full probability distributions, shouldn't we be able to always match confidence to accuracy? Why would this appear? And finally, when it comes to neuroevidence and what Yannick was talking about, so that is completely great, and that is a big problem for scheme 1, but it's completely consistent with scheme 2. So this is what this is showing, is that there's some sort of uncertainty readout from the visual cortex, but that's also what scheme 2 is saying. So, you know, there's no evidence within this line of work that it is a probabilistic representation necessarily versus just some sort of uncertainty that is not probabilistic. Okay, so this is a very long title here, but you know, the question is there a single study that falsifies scheme 2 and provides evidence for probabilistic perception? Is there a single thing out there that actually provides positive evidence? You know, perhaps there is, but I don't know about it. I have not seen a single study that convincingly or even suggestively goes against scheme 2. And you know, I actually, this is the scheme that I believe in, scheme 2. So we have actually tried to study this recently, and we have some evidence, admittedly very preliminary, against scheme 4. And this is work by my graduate student Jiwon Yeon, who is also about to graduate and is going to be on the job market. So how do you distinguish between scheme 4 versus schemes 1 to 3? Well, you could do that if you have a representation that is multimodal. So if you have, for example, 3 modes, scheme 4 would say you're representing all 3 modes, where scheme 1 to 3 would say that you only get to represent a single mode at a time. Okay, and you can do the same thing using discrete options, and that's much easier to do experimentally. So if you have 3 options, A, B, and C, a population model, which is what I'm going to call scheme 4 for the remainder of this talk, is going to represent all of the activities for each of the 3 options, versus a summary model would only represent a single one of the activity. So then how do you distinguish this? You can already hopefully see that this is actually tangible to do experimentally. So the way we did it is we had this paradigm where people fixated, then a stimulus appeared, and the stimulus consisted of a target color that was slightly more prevalent than the non-target colors. And on each trial, the target color was chosen randomly. Then the task was always, what is the most frequent color? And in one condition, all 4 options were available. And the other condition, we made only 2 options available, in this case, green and white. And we call this the 4 alternative and the 2 alternative conditions. And this is a block design. So we had a lot of subjects, but not a lot of trials per subject in this first experiment. So why do these models make different predictions? Well, if you think about the 4 alternative condition, they actually don't make alternative predictions. They're exactly the same. So whether you represent all 4 activities or you just represent the highest activity, it makes no difference because you always pick the highest activity as your answer. So the 2 models are actually completely equivalent in the 4 alternative condition, and that's great. Now, where the difference comes is in the 2 alternative condition. So if you represent all 4, but then you get asked about white and green, and blue was your highest, now you can just compare white and green, the activity in those 2. You can pick the highest, and you'll be correct more often than not. Versus in the summary model, you only represent the blue. You have no information to compare white and green, so you'd be pretty much a chance. So in the 2 alternative condition, what this shows is that the population model is going to predict higher accuracy than the summary model. So we can then compare the predictions of the models to the observations that we get from the data. So here's the analysis logic. So we're going to take the data from the 4 alternative condition. We're going to fit a model that explains that data, and the model is the simplest thing we could think about. So for each target color, we're going to fit the activation values for each of the 4 colors, and that's going to give us a bunch of parameters. And, that's a lot of parameters here, but the thing is, it is a common set of parameters for both models. So we're fitting the same sensory activation profile, regardless of whether it's the population or the summary model. Then once we have fit the model, whether we overfit or not is not important here. We have fitted to the 4 alternative condition, and then we apply it to the 2 alternative condition. And in the application, the population model makes predictions with no free parameters. The summary model makes predictions with no free parameters, right? So we're predicting the alternative condition without any free parameters. So what are the results? Well, we observed given accuracy in the 2 alternative condition, and the population model way overestimated this accuracy. The summary model was much better. So this is the differences for each subject. As you can see, the summary model slightly overestimates, but it's much better than the population model. And you can do model comparison. We're plotting AIC values because there's no free parameters. AIC, BIC, all of these are going to give the same answer. And you can see that the summary model is strongly preferred over the population model. Now we did the same thing in a different way. Rather than colors, we use symbols, and rather than 4, we use 6 alternatives. And in this experiment, we had fewer subjects, but a ton of trials per subject. We really wanted to get good single subject data. And we find the same result. The population model strongly overpredicts the observed accuracy, and this is the individual data. This time, the summary model slightly underpredicted it. So, who knows what's going on? But again, the summary model is just better than the population model. Finally, we did a third experiment where we tried to have a more continuous feature space. So what we did is we had 3 directions of motion within this moving stimulus. So hopefully this is going to display properly. So there's motion to the left, lower right, and upper right. I don't know if you're able to see it well, but these are 3 clouds of dots that are moving in different directions, and and people can do that pretty well. So it's the same idea again. You have a 3 alternative condition versus a 2 alternative condition, and we again had a lot of trials per subject, and we find the same results. The population model overpredicts the accuracy, and the summary model is much better. So this individual data, population model overpredicts the accuracy for most subjects. The summary model is much better. And again, the summary model wins here for 8 out of the 10 subjects. So to summarize, the population model failed to fit the data in any of the experiments. The summary model strongly outperformed the population model in all of the experiments. And perhaps this is the first direct evidence against scheme 4, at least that I'm aware of. Now, this is not a conclusive study. There's a lot of limitations. For example, none of the experiments had truly continuous features. And I think a lot of the we are talking about sort of assume a continuous feature space. And our experiment 3 actually got close to that. I don't think it was truly continuous, but that's something that we can build on. There's also the issue that there's potential short-term memory demand in the 2 alternative condition that was not present in the 4 alternative condition. We tried to minimize that. We showed the 2 options right after the stimulus presentation, and there was no delay, and it was a block design. But you can still argue that maybe there was some additional short-term memory demand that decreased the performance in that. Finally, we have been talking about the single stimulus on a single trial, and there are multiple stimuli here, so that's not ideal. And follow-ups, I'll be very interested to think about how you can do a similar thing with a single stimulus. I think the moving dots is one option, but that's what we're going to talk about in part 3. Finally, to conclude, scheme 1 can be rejected, but it doesn't mean, if you reject that, it doesn't mean perception is probabilistic. Hopefully that was very clear from part 1 already. perception may be probabilistic, but I have seen no evidence for it so far. And from my point of view, the onus of proof is on the foresight. Because of consciousness not being probabilistic, I think this non-probabilistic perception should be the default, and the foresight should really provide some positive evidence against it. Finally, there's some preliminary evidence against Scheme 4, and hopefully this also shows that this is empirically tractable line of empirically tractable. You can do studies, you can design studies that address this question of, at least Scheme 4 versus the rest of the schemes. Each study may have limitations. This one definitely does, but hopefully, as part of this collaboration, we can design better studies and converge on an answer. And that's all I have.
Now we'll have one more in team against, right?
Mm-hmm. One more team against.
Great.
Oh, let's see, I'll change this. All right, so this is going to be at a sort of more abstract level. I'm going to first just say something about the debate in the early 20th century between realism and instrumentalism about the atomic, about elementary particles. Ernst Mach and Pierre Duhem held that the evidence that they'd gotten so far should not dislodge you from a skeptical position. It says if there are electrons, but that doesn't show that there are electrons. Later in the 20th century, a number of philosophers argued pretty persuasively that it would be a miracle if the data come out just as if there are electrons, but there are no electrons. Hilary Putnam was a very strong proponent of this idea. And the instrumentalist view about the atomic nature of matter and about elementary particles just disappeared. And everybody realized that instrumentalism, or almost everybody realized that instrumentalism in that domain really wasn't a very good point of view. So one might think that the same exact ideas should apply to realism about the representation of probability. So we'd have the realist view that perception represents probability distributions, the instrumentalist view that it is as if perception represents probability distributions, and then the no miracles argument for realism would be, it would be a miracle if the data come out as if perception represents probability distributions if they did not actually do so. However, there is a big problem with this argument, which is that it wouldn't be a miracle. This is an area where the miracle argument does not work. Why is that? That is because evolution and natural selection favor Bayesian rationality in behavior. But if Bayesian rationality in behavior can be produced without probabilistic representations, that may be a cheaper way for nature to accomplish that. So it does not require representations of probability. Another way to think about this is to think about David Marr's three levels. The highest computational level, if you take a bird example, that would just be the basic outline of flight. The algorithmic level, the bird accomplishes that by flapping, and the implementational level, that flapping is realized by feathers. So here's the point. The computational level is instrumentalist with regard to probabilistic representation. And that's the level where evolutionary pressure applies. And quite a lot of people who do Bayesian perception recognize this and explicitly say that their theories are directed towards that computational level. So here's Tom Griffiths saying most Bayesian models of cognition are defined at Marr's computational level, characterizing the problem people are solving and its ideal solution. Such models make no direct claims about cognitive processes. That is, they don't make any claims about what Marr termed the algorithmic level. So they're just at that computational level, which is the as if level. So here is an example that illustrates this. This is an experiment done using pea plants. And the idea is that they took individual pea plants and divided their roots into two pots. And some pots had constant nutrients, some pots had variable nutrients, green for constant, red for variable. And in addition, some pots also had a rich environment, sufficient for the plant to flourish, and some plants did not on average. And the result was, you can see it here, that more roots grew in the constant one in the rich circumstances, rich nutrients, but more roots grew in the variable pot in the poor circumstances, low nutrients. Now, except for some kooks, I think we could all agree that given that plants don't have any nervous system and nobody's ever discovered any representations of probability, that the plants are not representing probabilities. And furthermore, they're not even representing means and variances. It's just as if they represent mean and variance. So we have an example of how nature can make organisms that act as if they have some aspect of uncertainty baked in. Here's another example. We're all familiar with the prior that light comes from above and slightly to the left. So these two stimuli are exactly the same, except this one's inverted. I just took this one, inverted it, and put it over here. But you can see that the items that look convex here look concave here, and that's because it's as if we have a prior that the probability is high, that light comes from above and slightly to the left. But I think most people nowadays think this is probably built into the architecture of the visual system rather than represented. And so we have this important distinction between what's built into the architecture and what's actually represented explicitly. So we might ask what would show that something is represented in the visual system rather than being baked into the architecture. And I think the idea that all of us panelists agreed to is that this is a matter of flexible use in a variety of circumstances. And architectural properties do not allow such flexible use. So I finished so much faster than my time. Let me say that I agree with what Dobie said. I also think that maybe this will get us started on our discussion, that the results that Janneke presented only show something is wrong with option 1 in Dobie's 4 cases. That is, it shows that we have more than a point estimate. We have point estimate with uncertainty. And that is far short of item 4, a full probability distribution. So I think I'm just going to stop there.
Great, thanks everybody. So why don't we bring all the panelists back on the stage and we can start our discussion. So before we go into the Q&A, maybe we can give the for side a chance to respond to the against side since they went first. Do you guys have any, or maybe a little bit of back and forth here, if there are any points that we want to pick on, would be nice to get us started on the discussion, and we can go to the audience questions. So for side, Rachel, Janneke, any comments?
Yeah, I think one comment I have about suboptimality, and I think I also like quickly browsed through the Q&A and the chats, so this was also something that other people brought up and we've discussed also offline between the four of us, I think, or at least Rachel and I have, is that, you know, suboptimal could be because you don't know the correct generative model, you don't have full knowledge of all that, and that create behavior that is suboptimal. But it doesn't mean that it's not a full probability distribution. It's suboptimal in terms of, you know, what you get out because you're using the wrong knowledge, but the knowledge itself is, you know, you do take into account more than just point estimates and more than just uncertainty.
Can you do that into a back and forth a little bit?
Sure.
Yeah, so I completely agree with that. And my counter argument to that is, well, if you have these really simple tasks in the lab that are way simpler than anything you're doing in the real world, and you can't even figure out the generative model for that task, well, what's your hope in the real world? And if you have no hope in the real world, then why even think and talk about probability distributions when you can't even do it properly in the lab?
So, but, you know, in the lab, you need a lot of exposure to a lot of stimuli to actually infer a generative model and to know that it's more complex than, say, for example, like Gaussian. I think the question is really like, have people have that much exposure? It becomes a statistical learning problem. I mean, people can do a lot of things, right? So I think it's,
Yeah, I mean, I agree with that. So there's certain features of the world that we get a lot of exposure to, like, is it vertical and horizontal orientations? We have a lot of exposure, and that's great. There's also a lot of features like seeing a bear and seeing a lion and seeing somebody who is going to stab you. Like, that's, I don't know how it went there, but like, you know, there's a lot of situations that there's not a lot of exposure that we have in the world. Maybe 0, maybe 1, maybe 2 exposures. So that seems a lot more difficult than the lab.
Yeah, but I think learning is not defined on a life, like on a lifetime, right? There's also such a thing as evolution. Some of those things you may have learned those, or, you know, through evolutionary pressure, like orientation receptive fields, for example. That could have happened for things like that as well. And those can be very complex, and we can learn them over very extended time scales, and then it all looks beautiful. Yeah.
Sure, it's not impossible.
Adam, Rachel, any comments to follow up?
Yeah, I'll just I'll bring up a couple points that I think can be addressed in a similar way from Dobie's arguments about. One was that because consciousness doesn't seem to be probabilistic, which we've all agreed on here, that should put the sort of burden of proof on the 4 team for saying that there is some kind of probabilistic representation, even if it doesn't make it to consciousness. And the other one, kind of a similar line, was people are bad at using probabilities in cognition. Like when you tell them explicitly about probabilistic information, people are sort of bad at doing arithmetic related to probabilities. And I think that, well, I agree with both of those points. First of all, that consciousness does not particularly have a probabilistic character, and that people are really bad at using probabilities. But I think what we're sort of trying to center the debate on the availability of information to do decisions. And I think we make a lot of decisions without any explicit or conscious knowledge about how we make those decisions. Fortunately, because usually when we do have very explicit or conscious knowledge of our uncertainty, it takes us a really long time to make decisions. So I think that just we want to focus our dispute, and I wish I had a hat to put on here, about these kind of decisions that can be made perhaps implicitly. The decision has to be explicit, but the machinery, the computation that leads to the decision may be very rich and very informative to help the decision be good.
One thing, I think that's a good reply to Dobie. One just slight addition to Dobie's point about how bad we are with probabilities in cognition. Years ago, a philosopher, Ian Hacking, wrote a history book in which he argued pretty persuasively, I thought, that at least in Europe, probabilistic reasoning wasn't discovered until medieval times or maybe early Renaissance times, and that in the ancient world, people were unable to understand games of chance. Anybody who understood probability could just win a ton of money if anybody did, because there was no population-wide understanding of probability. I mean, really, even elementary probability.
All right. So to kick us off then to the discussion, and we'll open it up to audience Q&A, maybe we can show the results of poll 2. And so this is the one that we had at the beginning of this debate. We can see after Dobie's first part 1 presentation, this was now the distribution, and it looks like maybe is perception probabilistic lost a couple people, and so maybe we're moving in this direction, I don't know. But we can also now do a third poll, which will be after seeing after seeing the for and against arguments really spelled out in detail. Which of these schemes now do you think is the right one, and have you changed your idea? So as we go through the audience Q&A, I'll leave this guy up, and then we can show, before we go into part 3, we can show the results. So any other questions or comments from the panelists before we go to the Q&A?
Well, I noticed that one of the questions in the Q&A is about something that all 4 of us have accepted, that conscious perception is not probabilistic. Richard Brown says, what are the reasons for thinking that conscious perception is not probabilistic? Yeah, so maybe we start there. And also, again, feel free to pick questions out of there. I'll read off the top voted ones if I have to, but if you guys want to pick some, then we can also do that. So yeah, let's start there. And let's hand Richard a microphone, and so he can join the conversation as well. So I think since Rachel has actually written on this topic, she should answer it.
How kind of you, Ned. Yes, I have written on this topic and argued that conscious perception is not probabilistic. And in those arguments, I made a distinction between having some notion of precision, a precision of an experience, a sense, some possible, that there can be more than a crisp single interpretation, and there can be some spread, but arguing that it is not probabilistic in the sense that you do not have the conscious awareness of there are simultaneously many possible interpretations that this one object could be, and you do not in your head carry around numbers saying, I think it's 30% likely that that's a trash can, and 40% likely that that's a I don't know, that's a tree stump, and whatever the remaining is, another 30% likely that that's a, that's the backside of a bear or something. Let's say you're in the dark. Okay, you're looking at a trash can in the dark. I think you don't simultaneously represent in conscious experience multiple perceptual interpretations and assign them values to indicate their likelihood. So that's roughly the argument. But indeed, as John Morrison mentioned in the chat, there are arguments out there that conscious perception is probabilistic. So this is not the whole story. But I think that the four of us at least agree with the position that conscious perception is not probabilistic. But yeah, please, everyone else, feel free to weigh in here.
I'll also point out while we're marinating on that Peter Koch had a similar question. So I'm actually going to hand him a microphone too. And I had a similar question too that was asked on my behalf in the Q&A. So I'll also be part of this conversation if we want to do that. Richard, do you disagree?
Yeah, no, so that was really helpful because I guess in my own, when I was thinking about this, I was kind of maybe mixing up, and to some degree, the question of whether there's indeterminacy in perceptual outputs with the question of whether they're probabilistic. And so Rachel's clarification sort of helps me understand more what the target is here. But still, I do sort of tend to wonder that some of this may depend on what your theory of consciousness is, because if the output, so if you can have unconscious representations that are probabilistic, and like if you have a certain view of consciousness whereby, like a higher order theory where you're aware of that and that renders it conscious or something like that, then that you may not experience it as probabilistic, but the thing which is conscious is a probabilistic representation. So I was wondering if maybe the answer here may depend a little bit on like what specific theory of consciousness you may endorse in the background.
Yeah, but look, if the higher order thought about the putatively probabilistic perceptual state, if that probability doesn't make it into the thought, then there wouldn't be a probability in consciousness, even on the higher order theory. It would be about a probabilistic state, but not itself probabilistic.
This, I think, is kind of related to Peter's question, because he was asking whether the probability has to be in the phenomenology or just in the conscious state. So on this way of reading it, the state which is conscious would be probabilistic, but it wouldn't be part of the phenomenology that it was probabilistic. So I don't know if that, Peter may speak for himself here, actually.
Yeah, I found this a hard one to grasp what this meant exactly. So if every one of the panelists agrees that conscious perception is not probabilistic, then maybe Rachel or Janneke could clarify by what according to them is probabilistic about perception. Is it simply the kind of processing that leads up to the percept, or is that unconscious percept that feeds into decisions that's still probabilistic? This is not fully clear to me.
Yeah, I think this is a one that needs to be clarified. I think when we're saying conscious perception, what we are referring to is the phenomenology. Does that everyone agree with that?
Yes, the phenomenology of perception. And I think what he said is right, that your view is that the probabilistic information is available for tasks, for decision. So even if it doesn't make it into the phenomenology of perception, it's still available for decision making. So I think that's the view of the yes team.
Mm-hmm. Yeah, I agree with that.
Me too.
And I think we mostly accept that this is a possibility. I think the argument that I and Ned are making is that, you're proposing one more step, which makes it less likely, right? But it's possible.
Right. I mean, I think the reason part of the reason we wanted to clarify that we weren't talking about phenomenology is because that seems like a different a different kind of debate than, and very difficult to address experimentally. And so we kind of wanted to put that question to the side in some sense for the purposes of the adversarial collaboration. But I think it's yeah, it's important to at least be clear on what we all mean when we say these things.
So in the chat, in the Q&A, Nick Shea says that the line we're taking seems to be consistent with scheme 3. Maybe we should ask him to elaborate that.
Okay, we've handed a mic to.
Okay, thanks, Ned. Thank you, Megan. So I was just picking up on Rachel's answer, which is that it doesn't seem like there are multiple possibilities. But if you just have a point estimate and a variance, then it might not seem there are multiple possibilities, because as to how the world is, you're only representing one possibility.
I think that is so it depends on how you consider the transformation between the information that's available in scheme 3 and phenomenology. The information that's available scheme 3, by definition, is a mean and a variance that can be converted into a full probability distribution, that the brain knows how to do that conversion. So if you then imagine that that full probability distribution is present in phenomenology, I think it, the question is exactly what that transformation is. So there could be a transformation of that full probability distribution in which you have, infinite perceptual interpretations present with likelihoods attached to them. If what you have in conscious experience is just a mean and a variance, I would say that is really more like scheme 2 because it hasn't been converted to that full probability distribution.
So I wasn't understanding the distinction between scheme 2 and scheme 3 correctly then. I thought it was enough to be in scheme 3 to have an explicit representation of mean and variance. And then it might be that with some additional information like a prior or a generative model downstream, you could construct probabilities for different bits of the distribution, but that needn't be represented in order to count as being scheme 3. But I mean, they're your distinctions, so I'll be guided by you on how.
Well, I think one thing that would be missing if you just have a mean and a variance is the information that the distribution is Gaussian. If you don't have that information, you can't convert it into a probability.
No, but that might be presupposed, that might be implicit in the way that downstream computations make use of those two represented pieces of information.
Right.
Anyway, that clarified it. Thank you very much.
And there's a couple comments that are kind of coming in the chat that I think are related to this too. Luigi is talking about having uncertain conscious perception, the location of something being tapped on the back, that maybe the uncertainty is not represented as like kind of a multi-stable percept, where it's like, 30% trash can, and then sometimes it seems like it jumps from a trash can to a stump or something like that. And Luigi, I hope I'm interpreting your question correctly, but that maybe uncertainty is another aspect of the qualitative experience in perception. And also, while we're talking about this, maybe we should open up the conversation to not just talk about vision, because there's a lot of other stuff that goes on in perception, and then it might be relevant to talk about non-visual percepts, and especially as we start to design experiments now in phase 3 of the workshop.
Yeah, thanks, Megan. Sorry, just to add one thing. So, because I've seen that, I mean, when we think about perception, the examples, especially the intuitive examples, are taken from vision. And that, I think, can be very misleading, because the examples that we tend to think of are ones in which, we have incredibly precise representations in some sense. And then we think, we end up saying, oh, well, then, all these conscious perceptions are, say, they lack uncertainty. But let's say, if we focus on other senses in which, say, we tend to be worse at, also say in normal circumstances, not just specifically in some contrived circumstances. So this actually can, I think, maybe can be more helpful also for experimental design.
Thanks, Luigi. Okay, so shall we move on from this question and do a couple more from the Q&A before we move to phase 3? How does that sound to you guys?
Did we get your answer, Megan, or your question?
I think so. I mean, it was really just about this difference between the computations that lead up to the phenomenological percept and the distinction between phenomenology and access consciousness, and how we're kind of where we draw the line for where the readout of a probabilistic representation or the representation of a probabilistic representation ought to be, versus whether like the content of phenomenology is actually probabilistic in that way. So I think we did, but thanks for checking. So why don't we go ahead and move on? There was actually one question that got very strongly upvoted, and then unfortunately there's this silly thing about Zoom where if a panelist responds in the comment thread, then it moves it to the answered column. So I'm going to go pull that one out to make sure that we get a chance to talk about it. This question is from Eros Dimoncelli, and I think it also relates to the experimental design that we will talk about next, which is, I'm not understanding the non-Gaussian distinction. Perhaps mean and covariance are sufficient representation of perceptual probabilities if one also allows them to be defined on variables that are non-linearly transformed from the stimulus space. And I think this relates to what Ned said about this assumption that a Gaussian kind of, or that the system might have an assumption of Gaussian representation such that a mean and a variance would be sufficient to transform into probabilities. So unfortunately, Ira is not here anymore, but maybe we can just very briefly address this to make sure that we're clear on how this might impact experimental design going forward.
Well, I think the overall point, Ira isn't really disagreeing with the overall point that I was making, which is that just having a mean and a variance is not sufficient all by itself. You need something that relates the mean and the variance to the probability distribution. So he's proposing something that would do it even in the case of a non-Gaussian distribution.
So I think what he's referring to is like maybe what is represented is a full probability distribution in the brain. It's just that it's a Gaussian distribution. So why do we make that distinction at all, right? And I think we all agree. And the reason why we made this distinction is because it's very difficult to distinguish between a full probability distribution that's Gaussian versus like any of the other schemes. So that's why we went for something a little bit more complex. But it's absolutely, like Eero is absolutely right. It may well be that everything is full probability distributions. It's all Gaussian, yeah. At least that's how I think about it. And I think Rachel may share this view. You know, we don't know what the real distribution is.
If I can jump in here. So yeah, so if you're only talking about Gaussian distributions, then it's tricky, because how do we know that it's probabilistic versus non-probabilistic, right? We depend on this assumption of optimality, which is a tricky assumption as we see, because you can have one number that, you know, some sort of strength of activity that you don't know how to convert into probabilities. You do something and it's not optimal, but it looks like you had the right thing and you knew how to do it, but you had the wrong generative model, the wrong prior. So it's the same result in the end. So you can't, if you only have Gaussian distributions, you can't distinguish between schemes 2, 3, and 4. It just there's just no meaningful distinction anymore.
Yeah, this question also brings up the question about transformation of variables, which I think is an important one. I think so far we've always been talking about world variables in the sort of metrics that we measure physically as experimenters. But it's quite possible that that there's some linear, it's very likely in many cases that there's a nonlinear transformation between the world variable and whatever the internal variable is. So that, I mean, this is a hard one. It's something we're going to have to think about. I think using multimodal distributions is a way around that. But if we use single mode distributions, we will have to think whether we can really disambiguate scheme 3 from scheme 4 or scheme 2 and 3 from 4, given the possibility that there's some internal transformation of variables. It's tricky.
Tuning curves, right? Could be that the tuning curves are the transformation with Gaussian noise on that. Or the filters, they're not the tuning curves. Anyhow.
Great. So we can do a couple more questions, but we want to leave time to do the experimental design phase. So would you guys like to move on, or do you want to do a few more Q&A?
I should probably move on in order to have time for the
Great. So before we do that, then you've asked me to end this poll and launch, or I'll show the results here at the end of the part 2 discussion. And so this is interesting. Either the audience has changed in its composition, or people are changing their minds, and we can go and look later to see what might be the case there. But it looks now like instead of schemes 3 and 4 being neck and neck, that we've got a slightly stronger support for scheme 3. So maybe Dobie and Ned, you're picking up a little steam here. We'll see. It's shifting in the right direction, at least.
One of my arguments was that nobody supports scheme 3, so it's only between scheme 2 and scheme 4. So that has evaporated now.
All right. Well,
so there's an interesting question in the Q&A from Matthias Michel for Rachel.
Sure. Yeah, we can do that. Let's go find. Is that all the way? Where is that? Is it from Matthias?
It's in my listing. It's the second question.
Yes. Sorry, I wasn't paying attention. Why don't we do that one before we move on then, if you'd like. So Matthias is asking, one of your arguments was the following: we know probabilities are represented in early sensory processing and can also be represented in cognition. If so, it'd be surprising if those representations suddenly disappeared in between, but it seems to me that you all accept that conscious perception is non-probabilistic in nature. If that's the case, aren't you committed to some level of perceptual representation that's not probabilistic? If yes, does this weaken your argument, since we should all already accept that probabilistic representations do disappear at some point since they don't contribute to phenomenology?
Yeah, sorry. So
long question, Matthias.
Okay, thanks, Matthias. When I'm talking about disappearing and reappearing, our argument was sort of in the sequence of processing in the brain. We think it's unlikely that there's a probabilistic representation at some stage, a probabilistic representation like a subsequent sequential stage or hierarchical stage of processing in the brain, but that it disappears, it becomes a point estimate or something like that, or a much more impoverished representation, let's say, in between. I think this question about transformation to conscious phenomenology is like orthogonal to that question. As we all know, unfortunately, we do not have a theory of how exactly neural activity gets sort of transformed into the ether, into our conscious phenomenology in terms of the precise character of that conscious phenomenology. So I think these are on different axes. These questions lie on different axes, and at any stage in the sequence of processing, you could get some transformation to phenomenology that's essentially a point estimate or much more impoverished. But we're not really talking about that kind of operation here. That's helpful.
I think you're not really responding to what I'm taking to be Matthias's point, which is that the fact that probability information can disappear, leaving only a point estimate, suggests that the probabilistic information is somehow separable from the value that's represented. And why can't that happen in between perception and cognition? Was that your point, Matthias?
Yes.
Yeah, I mean, I don't know quite what else to say, except that I think that you know, you're right. They were sort of claiming that there's some way in which conscious experience can become decoupled from probabilistic information, while at the same time there's probabilistic information present in the system. I just see that is a logical possibility, but I don't have, you know, with the absence of a clear theory of how phenomenology arises from neural activity, I'm not sure I could say much more about it.
Just a quick insert here, because this was never addressed. This argument we didn't get to address, but so the premise is you have probability distributions somewhere in the early, somewhere late, and they disappear in the middle. An alternative view is that at no point in the process do you ever have a probability distribution. You do not start with the probability distribution of a single percept. Then in cognition, you know, you have information, but it may not even have a probabilistic nature at that point. And then in action, again, you maybe represent multiple actions at the same time. It's not necessarily clear that this is probabilistic again. So an alternative view is that at no point in the whole process do you have true probability distributions.
Thanks.
All right, great. You have an endless supply of silly hats, Dobie. Okay, so with that, it seems like this is a good time to move into your stage 3, which is experimental ideas. And so do you guys have some slides for this you would like to present? Let me go ahead and do that.
Rachel is going to present.
I have some slides. Let me share. Okay, everyone see this one? Great. So this is part 3, experiment ideas, and hopefully very fun and interactive. And we would really like to have this be a very, you know, engaged discussion to generate exciting ideas about how to really resolve this debate in some way, or at least advance it. So again, the ultimate goal of this adversarial collaboration is to develop an experiment or line of experiments to advance this debate about probabilistic perception. And here, advancing the debate means generating data that will challenge either team 4, Yannicka and me, or team against, Dobie and Ned, forcing at least one of these teams to reconsider our positions. So to do this, we need to design an experiment where team 4 and team against make conflicting predictions. So we are following open science practices here by designing our experiment and making our predictions in advance via this very public forum, which with each team agreeing that certain outcomes of the experiment would indeed challenge their view. So the experimental design phase is really where the rubber meets the road in the adversarial collaboration. And we, as a group, are very much at the brainstorming stage. So we hope that all of you thoughtful and creative people will contribute to a guided brainstorming session with us right now over the next 30 minutes. So as Dobie discussed in part 1, we have articulated these 4 representational schemes to express a continuum between a representation with very little information, just a point estimate in scheme 1, all the way to a lot of information, full probability distribution in scheme 4. He's already described why we think that the most feasible boundary to attack experimentally is this one between scheme 3 and scheme 4. And again, knowing that the brain can't represent anything, including probability distributions, with infinite precision, for the purposes of this debate, we are focusing on a minimal version of scheme 4, which says that the representation is more than a point estimate and variance. So more than a point estimate plus variance is available to the system for flexible use in decision making. So our goal here is to design an experiment that will advance this debate by distinguishing schemes 1 through 3 from this minimal version of scheme 4. And we have stated the scientific question as follows. This is what, as Dobie already said, but just to remind everyone again, at the specific, somewhat wordy statement of the question, but we hope that it's at least precise enough to generate some experimental tractability. So the scientific question is, can humans perform flexible and deliberate computations that require access to more than summary statistics, and that is specifically more than mean and variance, of a perceptual likelihood function or posterior on a single trial basis? And for thinking through how we can answer this, I want to highlight the 3 requirements here. So this question has 3 important parts. First, flexible and deliberate. We want to make sure that the computations are not already baked into the system, as Ned would put it, before the experiment starts. Second, more than summary statistics. That is more than mean and variance. Effectively, this means experimentally that we think at least that we need to be in the regime of non-Gaussian distributions. But if people have ideas about how to say that there really is a probability distribution that's more than mean and variance even in the domain of Gaussian distributions, we would be interested to hear that. But so far, what we think amongst ourselves is that we would be in the best position to distinguish these 2 positions experimentally if we're in the regime of non-Gaussian distributions. And then finally, single trial basis. So we have to demonstrate that this information is available on a single trial. So there are a couple of considerations for the experimental design that we would love to discuss with all of you. First of all, the question, how can we generate a complex or non-Gaussian likelihood or posterior? And second, how can we determine what information is available on a single trial? So how can we show that there is more than mean and variance, for example, or how can we show that there's convincingly not more than mean and variance? So what I want to do right now is spend maybe 12-ish minutes on each of these 2 questions. I will tell you some thoughts we've had about how we might go about solving these experimental design problems. And then I'd love for you all to weigh in in the Q&A, and please look at the Q&A and upvote good ideas that we can then discuss together. And I think all of the panelists will be on video again, starting now, so that we can discuss this all together. Okay, so first of all, question number 1 is, how can we generate a complex likelihood or posterior? Again, we want to avoid a situation where cognitive knowledge of the prior could explain the results, which is why we've steered away from manipulations of the prior. But that's not the critical thing. The critical thing is that we want to avoid situations where cognitive knowledge could predict the experimental data rather than something that's generated perceptually. So, so here, just to sort of make things concrete, we have just 2 examples of some non-Gaussian distributions. Here's a bimodal distribution. This is a skewed distribution. So these would count as non-Gaussian or complex distributions for our purposes. So we have a few ideas of how to do this. One is to have a generative model that has enough complexity to generate these kinds of likelihoods. Another possibility is non-Gaussian tuning or non-Gaussian noise. Or finally, some sort of non-uniform modulation of the Gaussian measurement distribution using some other manipulation like adaptation, attention, or perceptual learning, maybe starting out with a Gaussian distribution that we modulate in some way so that it's no longer Gaussian. Okay, so that's, this is the first question, and I will just open it up back to the Q&A for a few minutes, and also if any of the other panelists want to weigh in at this point on specific examples that you might have in mind for any of these types of experimental manipulations.
Yeah, I just want to jump in here and say, personally, I'm most optimistic about having bimodal or trimodal distributions or something like that. But the other thing I want to say is that maybe the Q&A is going to be hard. We already have like 30-something questions. It's going to be hard to get upvoted. So if you have any ideas, maybe just raise hand, and Megan can just bring you.
Yeah, I was going to say exactly that. So we'll just do it that way, and that makes it easy. Can I actually start us off with a couple of the comments from the chat, just bring our attention there. I think an important distinction here is that the likelihood needs to be the thing that is multimodal or skewed, and that this can't be reliant on kind of sequential samples over time or multiple trials or something like that. There's a couple of comments about that. And so Dobie, maybe you could address Andre's question about, and Joey's comment about the study from your lab that had multimodally distributed stimuli, and whether that was a limitation, or whether that would be appropriate, and just do that study many times over, and maybe that can answer this question.
Yeah, so, that study was motivated by all of the considerations that they're having right now. I think the question is, how do we do that while removing the limitations of the study? How do we do that ideally with a single stimulus, while not having potentially more short-term memory demand in the two-choice condition and things like that? Yeah, I guess that's maybe for team 4, for probabilistic perception. Is there any kind of variation of that study that, if it found the same results, would convince you?
I think what is needed here is a generative model, and basically asking what an ideal observer would do, so inverting that generative model. So I think we need to compute from an ideal observer perspective what the likelihoods are, and see if those likelihoods are consistent with like a trimodal likelihood. I think that is, like, for any study that we do is going to be important. And the other comment that I have is that so you can create, I mean, you can have a trimodal distribution, like you can draw from a trimodal distribution over trials, but that could also be consistent with a model where there's a Gaussian likelihood or a Gaussian measurement distribution combined with prior knowledge that's trimodal. And I think it's important to make that distinction as well. That is going to constrain the kinds of experiments that we can do, the kinds of experiments that I personally would be convinced that would be would at least address this question. And like if we had any positive or negative results, would make me lean one way or the other, or more the other way, I suppose, than the way I'm already leaning. Mm-hmm.
I'll point out that Luigi raised his hand during this, and so we've handed him a microphone. So Luigi, do you want to?
Thanks. Yeah, thanks. Yeah, so let's say this is a point in which we say we can discuss a bit the proposals, or can I just, so let's say, because the issue, I completely agree with the point that we don't want to put things in the prior. So let's say, and so if you don't want to use the prior, what seems to me natural would be then to exploit a Q combination, as you know, a lot of people have done in the past. Mm-hmm. And especially because say what you want to do is to manipulate at least, you know, one of the, for example, one of the two, for example, the precision of one of the two, such that you can see what happens when you actually perform the decision, because that's, again, that's one of the standard manipulations that you want to do. So for example, one, say off the top of my head, what I would start playing around is, suppose, okay, so you have a vision and audition, but let's say now you want to make one of the two non-spatially equal. They're already not spatially equal, we know, but let's say, you know, you want to enhance the fact that the likelihood, say the precision changes according to the angle, okay? And you want it to change drastically such that, and if it does drastically, according to the maths, then the likelihood is going to be skewed, okay? So, and I mean, I say again, I'm not an expert on hearing, but I say I can imagine that, for example, if someone, you know, one of the ears is covered or stuff like that, this will introduce a strong anisotropy in the space. I mean, I'm just making this example, but saying probably other ways to introduce a strong anisotropy in the space, which, you know, might actually then introduce, I mean, say, according to the math, should produce some, say, at least skewed likelihoods. Then, you know, you can play around with those, for example. And the nice thing about the skewed likelihood is that whether, you know, so then you can change the precision of vision. So let's say we have these skewed auditory likelihoods. Then you can change the precision of vision, and depending on whether you're, say, to the left or to the right of the stimulus, because of this skewedness, the effects in manipulating the precision will be different, right? You'll be biased more or less depending on the skew. I don't know, probably I wasn't very clear, but I hope that someone got the
that sounds very promising. I just, can you say a little bit more about how you're making that likelihood skewed?
So, I mean, I say the example I had in mind, but I say here, you know, we would probably need someone who's a bit more an expert in terms of hearing, and say, you know, and which I'm not. But I say what I'm thinking is, say, so if you're simulating, for example, you know, say being deaf, you know, covering your one of the ears, then I say I can imagine that my spatial perception is going to be incredibly, well, first of all, worsened, and then I say also very different whether it's one side rather than the other. So I expect this change to be anisotropic. I mean, that's my expectation. Maybe I'm wrong. And even this specific example of how to manipulate hearing is wrong. I can imagine that, say, there must be a way to, say, manipulate our perception I think in an ecological way. So I think it's important to do it in an ecological way, such that we can imagine that the brain is not completely dumbfounded by what's happening, but still, you know, it's kind of able to, you know, devise some, say, a response which makes sense. Because if it's completely confused, then we can imagine the brain will simply fail because people don't know what to do, the brain doesn't know what to do, etc. So yeah, this is kind of my proposal.
Yeah, that sounds promising to me. I think if for example, if we put something in one ear, and you mostly get sound from here, not much from here, and if that actually creates a skewed likelihood for locating the sound, that sounds promising. I guess it really relies on the manipulation actually working. I guess if you have ideas about who we can talk to, or if you wanna brainstorm together, I think we'll be welcoming to people who have ideas, and you can join the team and stuff.
One of the benefits of this program is if you want to be on the team, maybe that'll happen. But I would like to point out also that in discussing this kind of transformation and presentation of skewed likelihoods, that Steve has a point in the chat. Steve Fleming has a point saying that it seems like a non-Gaussian or skewed likelihood in the space of the stimulus measurement is problematic, as a potentially unknown transformation could still mean it's internally represented as a Gaussian, which was similar to Eero's point before. So it feels like the types of manipulations that Luigi is talking about might need to be accompanied by some sort of independent measurement of what you've actually done to the likelihood, if that could even be possible.
Mm-hmm.
So my reaction, I say yes, I agree with the problem, but I say what I would then say is that if you, let's say, again, this is off the top of my head, so I haven't thought this very thoroughly, but I'd say maybe you can do several, then, well, I wouldn't say this would be a single experiment, but just like, these are several papers, but I'd say you can then test by doing several manipulations at this, say, at the same time, or on the same group, which are different manipulations, which produce different altered likelihoods. And then, I think they say then it becomes harder. I mean, let's say to say that the brain is keeping the same representation, then, of course, say it's possible the brain is changing representation to keep a Gaussian representation of a different nonlinear transformation. But then at the point, they say distinction becomes moot. In the sense, okay, if the brain can do that, then it can effectively represent, things which are non-Gaussian in different spaces. So, I mean, that would be my response.
And there was a similar question from Rob, and he's requested that he join the conversation. So Rob, did you have something you wanted to add?
Sure. Hi, everybody. Thanks for doing this. I agree with the point Eero made earlier, that the distinction between option 3 and option 4 seems a little bit hard to make, right? Once you have a Gaussian distribution to work with, it's often very easy to transform that into a more complex thing. Like if you were to combine two Gaussians, now you have your bimodal. Or if you use a quadratic transformation, you can turn it into a bimodal. So what makes you guys think that this is a meaningful and a fundamental line between option 3 and option 4 here? I do understand how taking uncertainty into account, yes or no, that's fundamental. But once you've crossed that line, why is it important to know whether it's option 3 or option 4, and where do you recognize that border?
So
yeah, that's a difficult question, and we're trying to understand it. From my perspective, what I see in the literature is that we reject scheme 1 and therefore then start building very complex models like probabilistic population codes and neurosampling, which may as well be true, but they seem to be making stronger assumptions that are actually experimentally testable. Now, yeah, I think you need to be. It's not a priori clear that scheme 3 and scheme 4 are distinguishable. It is possible that they're not distinguishable either. But I think there's a possibility there they're distinguishable. It's true that once you have, you can say that a given percept is represented by two Gaussians, right? You have two sets of point estimate and a variance. I think that's actually a little unlikely. I think that again goes against the way I see a single percept. So if you can show that that would falsify, I think that would falsify at least a simple version of scheme 2. And that would convince one person out there that they're wrong. I don't know if that's a good motivation to do science, but.
Can I add something? Because I actually really agree with Arrow and with Robbie. It may well be that everything is Gaussian in the brain. It's a question I've asked myself a lot, just how complex need it be? So in that sense, it's going to be difficult. It could still be probabilistic. It could still be a full probability distribution, but it could be a Gaussian. And then if that is the case, it will be very difficult to really address this with the particular distinction that we made, or even like within this collaboration. But I think a reasonable question, I do think it's a reasonable question to ask whether or not it is more complex than a Gaussian. And that is something we can try to address here. Mm-hmm.
So can I add one thing?
Mm-hmm.
Thanks. So responding to Robbie, so I completely agree that if you think in terms of transformations, yes, of course, say once you have a Gaussian, you have everything. So to me personally, say if you want to really make the distinction between 3 and 4, it boils down again to how flexible this representation is, or these transformations are. So let's say, so if we have a fixed transformation that transforms a Gaussian into something else, but then we are constrained to always have that transformation, then let's say, okay, well, then maybe it's like having a Gaussian, but if we have a Gaussian, but then we can keep changing transformation depending on the circumstances, then it looks like we have a more, we have a richer representation in some way. So for me, it boils down pretty much to that, how flexible and rich is this representation, or can be.
We have some other comments in the chat as well to keep this going. And I'll remind people, if you want to join the conversation and unmute your microphone, just raise your hand and we'll do that. So
I also just noticed that we're getting pretty close to 2 o'clock, so at some point we could also go on to number 2.
Sure.
Here.
Yeah. I didn't. Yeah.
But,
sure.
If there's a questions that are upvoted in the Q&A, anything else, do you think we should go on to number 2 now?
So why don't we move on to number 2? I thought we were close to the end there, so yeah, let's go ahead and go on. Yeah, good.
This is the number 2 and the last number, but the question of how can we determine what information is available on a single trial, something that we are wrestling with now and would love to have your input on. So we want to design an experiment where the probability distribution, if it is available, would be reflected in some behavior. And these are different kinds of behaviors that we have been thinking about. Designing a task where it's obvious from the decision rule what information is available, and what is taken into account in the decision rule. Perhaps using confidence reports to get a sense of what information is available to the observer to make this kind of more metacognitive judgment, including multiple guesses, or maybe even explicit distributional reports. In other words, asking people for richer reports than the typical kind of 2AFC binary choice. And maybe there are other options. So we can keep talking about question 1 and question 2, I think, here. So if anyone has thoughts on either one, feel free to weigh in.
I think this flows really nicely from the conversation that we were just having. Ralph, I'm not sure whether Q means that you have a question.
Yeah, I'm going to abuse my power as a co-host here to chime in with 2 points. I mean, maybe to this last slide, right? If you want to probe a probability distribution, one way to do so is to take many moments of it. And in the context of Bayesian decision making, that means probing it with different reward functions or loss functions. So if you have the same experiment and you can get subjects to do different reports in response to different loss functions, I think that also relates to Ulrich Barholm's point about transfer, then that would be strong evidence that there is some, at least the knowledge about an underlying probability distribution present in the brain, even if that leaves, unanswered somewhat the link to, perception. But the other point I wanted to make is, and it also came up several times, I think it's really important to think about what is perception, what's the variable here? I mean, what's the chance the brain uses Gaussian distributions? Some, I don't know, something we've made up, someone a couple of hundred years up, years ago made up. And so, why continuous variables? Why not, discrete variables? Do we really perceive a continuous orientation? I don't. Should we think about binary variables or discrete variables in general? And if you think of a binary distribution, there's one number that's enough to represent the whole distribution, right? Absence or presence of a little Gabor-shaped feature in V1. And so, I don't know, for you who were in the probabilistic computations workshop, I mean, we know already that, the choice of this variable can determine the answer. Like, is it a parametric code or is it a sampling-based code? Maybe it's even relevant for the question. Maybe it's deterministic for one variable, but then looks probabilistic because those deterministic responses contain the information with respect to another variable. So anyway, I don't have the answers, but I think these might be important questions to consider.
You guys have any comments on that? And I see that Weiji has his hand up too, but
one
response.
I actually think that if we allow ourselves to go into discrete choices, I think there we can do experiments much more easily, because it's very easy to do distributions that are this is not Gaussian, right? If you have 3, 4, or 4 options, Gaussian doesn't even apply. And maybe you can manipulate experimentally more easily the shape of the distribution, what out of the 4 options, this more likely, this less likely.
But I think that it's important to distinguish between the internal subjective variables that the brain has learned about the outside world and what we manipulate in the external world. Right? I'm not talking about, we can do anything in the external world. We can make up orientation or motion direction, but that, the question about what is perception over, or what may be represented by the neural implementation, these are empirical questions, and the answers, it's not obvious what the correspondence is between the internal representation and the, whatever you do in your experiment. So I think it's important to keep that apart too.
No, absolutely, and that's where the experimental design needs to come in, to probe what is actually represented on a single trial for a single stimulus. It shouldn't be across trials, and it shouldn't be just long-term learning and long-term priors and things like that.
Yeah, I mean, I think it's a very deep question, and to the extent that we can articulate different possibilities for what the perceptual variables are, and then relate them to the predictions that they would make under one scheme or another, I think that would be really helpful. At the end, we might find that we can rule out certain interpretations of the perceptual variables and how they relate to the schemes, but not other interpretations of how, what different options for what the variables are and how they relate to the schemes. So, but I think the conceptual work of trying to articulate these options would be really, really useful for us.
And we have 2 hands up, maybe before we finish up here, Weiji, and then Eric DeWitt.
Thank you. Yeah, so I've been in this business of trying to show evidence for probabilistic representations for maybe 17 years now or so. It actually started in a collaboration with Ulrich. And I've sort of become very frustrated with actually how hard it is to already find evidence for just uncertainty being taken into account in decisions. And all of you know that, and you've done similar work. So if you fit real experimental data, you always have to think of all those nasty, unpleasant complications like the stimulus dependence of the noise, the shape of the priors, decision noise, wrong assumptions that the observer might be making. And all of those are going to make your conclusions about the representation of uncertainty more murky and less clear. And if you're taking this a step further, like you guys are suggesting, to distinguish between Gaussian and non-Gaussian likelihood functions, to be completely frank with you, that is not a research agenda that I would wish upon anybody. This is going to be a lot of suffering for potentially lots of inconclusive papers.
Any follow-up comments, guys, before we go to the last comment from Eric?
Such an optimistic note to end on.
Sorry.
What do you suggest, Weiji?
Yeah, so I love this in theory, but I'm just skeptical if this is going to work in practice. And if the outcome of the discussion is that it might not be worth making this fine distinction along the lines of what Robert was also commenting on, then maybe we have to redirect the research agenda.
I think that maybe the result, and I think that would still be a very useful realization. I would argue that if this is all we know, that uncertainty is represented, and we have no idea how, maybe that's all we can know at this point. And any theorizing on top of that should always come with the caveat that it's theorizing, right? It's one possibility, but we don't have evidence for that. I think if we, in this visible collaboration, even if we come to that conclusion, I think that's still progress, because right now, Weiji, you've come to that conclusion, but I don't know if the rest of the field, if that's obvious to everybody. I think the four of us have a little bit of hope still, so I guess we're not.
I'd love to be proven wrong, Dobie. I'd love to be proven wrong.
All right, we've got a couple more questions here, or comments from Eric DeWitt first, and then from another person who, could you change your name actually so that I can call on you by name, axler@gmail.com, and then we'll finish up.
So it's quite hard to follow up on Weiji's comment, but I guess I'd sort of been wanting to specifically comment on the slide, and then maybe I'll also try to take an optimistic spin on what Weiji said, and maybe a couple of other things. So I just feel like one of the things, and also having done some of these kinds of human experiments, trying to look for confidence or probabilistic judgments, one of the things that's always concerned me about our desire to have sort of control using standard approaches like 2AFC is that it does force the system, the subject, to collapse whatever representation they have for your report. And so I guess whatever mode you would like, whatever you'd like to see, whether it's a single mode with variance or multimodal, you need to really think very carefully about the way the subjects are asked to behave, such that they're not forced into trying to use a point estimate. And this echoes, I think, some of the other things that have been said, but it just seems like you could end up shooting yourself in the foot by, hiding what would potentially be there, or at least making it hard to interpret. So that was the comment. And then I guess one thing that has come up a couple of times is that it seems that people believe, looking at the polls, like there's strong inference for probabilistic information being carried around in the brain and the system, but then we end up debating a little bit more about whether it's true at the perceptual level or at the conscious perceptual level. And maybe the result of Weiji's comments and the way to think about one of the goals here would be to decide, actually there's a place where that question may be ill-posed, and maybe it's ill-posed because we don't yet have a good way of defining what those boundaries are. I mean, that's come up a number of times in this discussion. So maybe if the panelists all believe that there is this probabilistic information available, you could divide the question up into what do we actually, I mean, you've sort of defined it very narrowly, especially with the single stimulus. What do we want to do as a productive thing for the community to try to help enlighten how we talk about these things? Maybe we'll make it less troublesome to talk about it, where there'll be clear distinctions. Maybe something like that would also assuage Weiji, I don't know.
I'm open to.
Sorry, Weiji, you got remuted. What were you saying?
And I'm just saying I'm open to it, and this also relates to what Ulrich was saying. Sometimes you just have to already simulate the experiment in advance and take into account the nasty complications. And if you can still come up with a clear distinction, then I'll be a little bit more convinced.
All right, maybe we do one last question here or comment from Zvi Ashler. I hope I pronounced that okay.
Yeah, that's fine. Thank you. I think there are ways to encode and to model uncertainty without the distributions, where, for example, in a generative type model, where it pulls, when it gets a piece of information, it pulls everything that uses it, tries to reconstruct it back, and then from that decides on the probability of which which perceptual object it may be. And it's hard to explain kind of on one foot like this, but there are connectionist models that can do generative kind of estimation of distribution during recognition that can give you a kind of probabilistic measure of how likely each input belongs when you're making that decision. And I can put a link on here for you guys, but it seems like everybody's looking at the distributions, but there's ways to estimate the distributions through a connectionist network, not by saying this is Gaussian or not, but just by looking at a generative model. And so I just wanted to point that out. Maybe that might be something interesting to you guys. And I just posted the link right there.
Yeah, thanks for that. And thanks for the link. I think it's really interesting to think about different ways that some kind of generative model could be implemented in the brain, it seems like there are different options to consider for how that implementation might happen, and then each one of those implementations would make different kinds of information available for other areas to use, and so yeah, so I think it's worth us thinking about what are those different implementational options, how would they inform what information would ultimately be available, how do those fit into these different schemes that we've articulated so far, if they do, or if we need to sort of make different sub schemes or new schemes. So that's very helpful. Thank you.
Great. Well, thanks all for the great discussion. So what we can do is let's formally wrap up here, and then if people do want to stick around, we can leave the webinar open and pull people kind of on stage so you can have a more naturalistic discussion if you'd like, and that's up to the panelists, of course, if they want to stick around too. But Rachel, I'm going to kick you off the screen here very briefly, and just put this slide up, which is the the next sorry, give me 1 second. the next GAC, well, maybe I won't do it. Maybe I won't bother. Basically, we have another one of these coming up tomorrow morning, starting at 6 a.m. Pacific, 9 a.m. Eastern, and a more reasonable time in Europe. And so that one will be about categorical inference. And so please come back for the next one. It will be great fun. And then we have 2 more of these on Friday, also at 6 a.m. Pacific. And then again at, I believe it's 9:30 Pacific, and then you can do the math for your own time zone there, but it's all on the website. So thanks to all of our panelists for a great discussion and for all of the audience members for participating. And before we end up leaving, I would like to do one last of these things because they asked me to do so. So before you get out of here, if you haven't left already, please finalize your answers in the poll. And then we can leave this Zoom open if you guys would like, and we can have you guys continue the discussion if you would like to. So
thanks so much for your help with everything and running this great meeting.
This has been really fun. Great, good discussion. Adobe's hats are fantastic.
Thank you also, Ralph.
So
thank you all.
Yeah, this is great. So what we can do now is if there are folks who would like to stick around, or if you guys would like to stick around, we can have people raise their hands. We can also give people co-host privileges, so you can actually pull people on stage. So Weiji and Eric, if you want to be on stage, but also don't feel obligated to do this. This is up to you guys if you want to stick around. So what would you like? Anybody
I have a 3 o'clock meeting, a 4:30 meeting, and a 5 meeting. So I think I'm going to go.
Fair enough.
I'm open to sticking around if anybody has if anybody wants to chat.
I just wanted to say hi Yannick, hi Ralph, hi Adobe, hi Megan.
Hi.
This is great.
This
I
is
had
fun.
to step out in the middle, but the first and the last part were fantastic. I don't know if Edgar mentioned it, but with his data, we can potentially try to distinguish 3 and 4, because in these likelihood functions that he decodes from V1, and maybe Janneke, that's also true for you. They spontaneously look non-Gaussian in many cases.
Yeah, for us too.
Yeah. So then you could, in principle, just test the full likelihood model for downstream plugged into a downstream computation against the model where you plug in the Gaussian approximation to the likelihood function into the downstream computation. Yeah, it's relatively easy to do. I don't know if Edgar is still here, but yeah, that's what I was thinking of. Edgar is thinks that maybe at the low contrast you can distinguish.
Yeah, guys, I think you guys should really do it.
So, yeah. If I can put in a plug or throw a wrench into the discussion. So one thing that we're trying to argue is there's really 2 different perspectives here, Gaussian, like a Bayesian encoding versus a Bayesian decoding view, right? So trying to decode some variable from neural responses, let's say, or fMRI, whatever it is, may look very different than what is actually encoded by the brain, trying to infer some higher level latents that explain the sensory inputs. So for instance, exactly. So, like if you think of V1 as representing intensities of Gabor-shaped features or absence or presence or something, that's quite a different thing from trying to decode orientation of some pattern that you show, which is presumably different if that's a Gaussian noise pattern or just a grading or maybe a house or a face. And so it's important to keep them, separate and can compare apples with apples.
Yeah, so Ralph, I read your paper on this. I think that distinction is useful. When I talk about it, it's always on the decoding side, as you know. I also take your point that these are not necessarily compatible. So if you have, let's say, a smart generative model where the brain actually, where what looks like noise is not actually noise, but it's itself some kind of smart probabilistic representation of outside uncertainty, then you can still do a PPC type decoding on top of that. And I think that's what we're talking about here.
Yeah. So anyway, these are all really hard questions. And I think before jumping onto the next experiment, I think it would be really useful if whatever paper you guys come up with just comes up with some systematic, right? And then people can still criticize it or whatever, or reject it. But to clarify the thinking in everybody's mind and making sure that there won't be a false debate between, let's say, all false dichotomies that may actually be complementary.
Mm-hmm.
So can I jump in to say something? Because I guess I'm approaching this from like a behavioral, like studying, not perception, but working memory. And I kind of feel like there's evidence that I have that suggests something like at least something akin to probabilistic representations. So in one paradigm, I have them just generate an explicit probability distribution by placing discrete Gabors over a color space for they're shown a color item, then they're tested over a color working memory space, and then they create a distribution over that color. And we find that as they place more and more of these distributions, it changes the center of mass of the reports and they actually become more accurate. So at least that suggests that the first report is not capturing all the information, and that you're getting more and more information as you get a richer, more complex report from people. And that's not explained by motor noise. And in cases where it seems like people completely report far away, or report over the identity of another item, if you give them more chance to fill out the distribution, they will put a higher center of mass of the probability distribution over the correct item, which does suggest that even though the reports kind of look like either a misreported item or a falsely, like a complete errant guess, that there is some target encoding, suggesting that either the report's wrong in some way, or that there's something more complex being encoded there. And that could, in the case of swaps, it could be like, I don't know which of these two items are there. It could have been this, or it could have been that. And to me, that feels at least sort of like a probabilistic distribution, right? If your belief is not, it was either A or B, it was either, it was either A or B. And in other cases, you can do things like, let's say people make a continuous report about something, and they're wrong. Let's say they're way off in what color they report. You can then give them a 2AFC of the correct color and a FOIL that's equally far from what they've chosen. So you're giving them two choices that are centered on what they believe, what they reported, and they will often choose the correct value, which again suggests that there might be something more complex that people are encoding, even though that their response is something like a discrete value in, say, these tasks. And so I guess I'm more like suggesting that we can try to do more richer response methods to try to get it. And again, this is all in the area of working memory. I didn't realize this was sort of a debate in perception.
So Daryl,
yeah.
I have a question about that. So can't there be information in working memory that doesn't come from the perceptual representation itself? Like, for example, from the reaction time or how smooth the subject's response is?
Can I actually follow up on that a little bit as well? So I've talked to Tim Brady about these studies, and I agree that this is like very promising. But what you have in those studies is, working memory, so several items. And the thing that is not convincing to me is whether the same thing would happen if you only had a single item. And I think if you can show the same kind of effects with a single item, I think at least for me, that would be very convincing. But when you have multiple items to remember in the first place, there's all kinds of interactions that may be happening that lead to these results. That it's not just the perception of each item is probabilistic. It could be that as the interaction between the items creates these effects.
So that's fair, and you guys are sort of focusing here on perception, but I would say that one way to approach this would be to take the response methods that you're using and open them up to be more rich and to be more complex. Because if the question is, are people encoding complex representations, we need to embrace complex reporting methods to try to see if given that choice, given the chance to convey information in that complex manner, extra information seems to be conveyed.
No, absolutely. I think that the things that you did in those studies where you gave a second option and you asked them to draw probability distribution and things like that. I think all of that is on the table for us. Yeah.
Yeah. So I would be a bit. Hi, Daryl, and I'm glad to hear from you and that this seems to be working in your hands. The thing that I would be worried about a little bit is how naturalistic this becomes, right? Because of course, none of what this is probably very naturalistic. Drawing a probability distribution really calls upon very high level cognitive knowledge, right? It requires that you know this concept and you have some basic math training. So I'm not even sure if this would reflect sort of the natural perceptual knowledge that people would have, as opposed to with, like, lots of cognitive influences worked in there as well.
I mean, I guess
I wanted
just, okay, go ahead.
Go ahead.
No, I mean, that's a fair point. I mean, we find that people report a cross-trial error distribution that sort of matches the within-trial error distribution. That is, the average of within-trial distributions really closely matches the aggregate error. But yeah, it's true that these are not going to be probably the exact thing that is encoded. There's going to be cognitive steps in reporting this, but if anything, that just sort of works against this. So if you find evidence that they're getting an advantage by using this rich report method, I don't think that the suggestion that this is somewhat artificial is too big of a problem, because yeah, it'd be great if we could actually read out the internal probability distribution. Maybe we're getting there with neural measures, but I don't think that because that is difficult that we should give up on trying to do that with behavioral methods. There's probably better ways to do it than the way I'm doing it. But I think that's the kind of thing we should try. We should try to really capture as much of the probability and not just do complex decision rules that get reduced to a discrete response. I think just getting a very full report is the better strategy.
Yeah, I mean, I said this in the chat and when I was speaking, and I feel like this is there's two things that I worry here may affect the kinds of behavioral outcomes that you guys could get out of an experiment. And one of them is, if you don't have a behavioral output that really allows the system to reveal that it's carrying around this distributional information, I think it'd be very easy to falsely believe it wasn't there. The second problem is, if we think about the vast resources for producing a behavioral report that a human brings to any task, a one-dimensional stimulus identification in some sense, which is what you're proposing, allows the human to do lots and lots of, apply lots and lots of heuristics or strategies that you may not want them to, and that you may have, I think this is part of what Weiji was saying, that you'll have a hard time modeling out or ruling out, right? So one of the things that was interesting to me is in the example, I can't remember now, I think it was Yannick who presented it. You're driving, a car down the road. This is a natural sort of perceptual task that people engage in all the time, where you have to actually track lots of perceptual objects, and you're not able to foveate or attend to all of them. And if they were perceptually sort of point estimates, using a caricature here, you would expect that over time you'd have lots of jumps and discontinuities, because actually you'd be carrying around locally error-prone representations of all these things. And we don't perceive things that way. A natural way of thinking about this would be, actually we're carrying around sort of distributional approximations of this information, and when we attend to them or we need to react to them, we collapse them into something that is a stronger point estimate. So as a cartoon model of why this is a sort of tricky area of research, it seems that the reasons that you want to carry around probability distributions are largely in places where you have multiple stimuli, multiple competing stimuli, and a decision rule that might actually have to, marginalize correctly in order to produce an outcome like not running into a car or a dog or something. So I guess one of the things that you guys might want to also think about is, maybe by trying to focus this definition for this question so narrowly, you might be shooting yourselves a little bit again in the foot, or at least that would be a worry I'd have.
Can I briefly chime in? I mean, maybe this is not what you were saying, because I was only maybe freely associating, but what I just heard you say is something like, if you only had a point estimate of some, internal representation of the outside world, then under many situations, and I totally agree, you would expect that point estimate to have discontinuous jumps and not change continuously.
Well, so just to be specific, so that it would be the statement over time in a case where you're tracking, multiple things where you have uncertainty over all of them.
I'm just trying to recast what you're saying. Right? So, for instance, if your distribution, your belief is bimodal, as you would have for a Necker cube, or for in many situations that are more complex, then if, let's say, you only represent the map, the maximum a posteriori, then the distribution may be changing continuously, but any one point, estimate or summary statistic or whatever may actually, behave discontinuously. Like I always find it very hard to think about, okay, how can I quantify perception? And so, yeah, decisions are one way, but decisions, they bring, a lot more baggage, like all the cognitive stuff to it, all the decision-making system, and, and so I wonder whether this, continuity versus discontinuity idea might allow for some novel behavioral, readouts of the internal percept that are better than just a button press or, a dial or something. That's all I want to say.
But why would it be discontinuous? Because, I guess you could just average those 2 point estimates, right? Or have some sort of, you could do something like that, and then it would be continuous. It would be off, but it would still be. So I don't see why it would jump around.
Well, if in any one moment, instantaneously, you represent a point estimate, let's say the map of a distribution, rather than the full distribution, then you can easily construct situations where that would jump around. For instance,
so like you gave an example, which I think is a good one, right? So there are a number of bistable perceptual illusions where you can have instances which, from a perceptual standpoint, you either have oscillating, sort of smoothly oscillating, or you can have jumps in your perception, right? It can basically change from one inference to another. And so if that is an example of having, basically due to noise or drift or whatever, your map estimate suddenly jumping from one mode to another, I think that's an existence proof. My point was that in our normal flow of behavior, when we're moving through the world, like what we have is a really enormous sensory manifold, right? That is extremely high dimensional. And I don't think anybody is claiming that we're carrying around all of the information about all of the things there all the time, but we're keeping some estimates of them, presumably. So, people who are moving through a crowded room and there's a chair there will naturally avoid it. They may not. I'm trying to avoid the word conscious perception here, so leaving that aside completely. You're carrying around some lower dimensional or lower resolution representation. And here's where the word perception, I think, gets tricky, right? So when we think of these visual illusions, we ask the subject to report, was it coming towards you or going away from you? Or in this case, did you see the chair or not see the chair? So we tend to try to collapse in one moment in time the information that was there to some, point estimate report. What I guess I wanted to say was that, I guess from the subjective experience point of view, we don't see those kinds of discontinuities normally in our perceptual experience, except usually when we get into these weird situations that are constructed like optical illusions. And so, I don't know, to me that implies either we're carrying around uncertain and noisy point estimates that are not jumping around in our perceived experience, or we're doing something that is keeping an uncollapsed representation of those things, and only when we attend to them and foveate on them or need to, form a behavioral decision do we collapse them. I don't know where that fits in the information exists to perception line, right? So that's the problem to me, is that's a continuum where we're trying to find good carving joint, and I don't feel like from the discussion so far, I found that we've found that. I seem that I'm not being clear to you though. So maybe you ask your question again in a different way and I'll try to.
Oh, I think I was, so basically, so I can see that from a book, but if you have a bimodal distribution, and sure, because of noise, one of the peaks could become higher and like if you take the map, your perception jumps around. But I'm a little confused as to why, like for the periphery, sure, like that's like there's going to be more uncertainty there. It could be a whole distribution, like the distribution is wider. I agree with all that. I just don't see how that would jump around. But I don't see how that is related to jumping around steps. Yeah.
Yeah, so this is at the level of a thought experiment, which is to say, if I had a point estimate that had been chosen, 10 milliseconds ago from one, noisy estimate, and then I attend to it again briefly, and it was very off, that because of the, particular noise at that moment, then the next time I attend to it, the percept would be in a different, have a different map estimate. And
I get what you mean. You're saying like it's already a map estimate as opposed to because it's already read out. Okay, that's the part I didn't get. Yeah. Okay.
Well, I'm now speaking here at the level of subjective experience, which in I guess my own, now I'm bringing a bias in, like regardless of whether I don't know, the word consciousness is so complicated, but once you get to that level, clearly internally you've done some kind of readout, right? It's available for behavior and for reporting to you people what I saw. So at that level, it seems you must have done something. And so I did an experiment. I mean, I mentioned that I'd done some experiments like this. So we were doing, a change, subliminal detection experiment looking at confidence measures. And we also did some manipulations to try to push people's confidence measures around. And what we found was that in like a gambling, a hold weight choice measure of confidence, we saw changes that were being pushed around, but in the actual reaction times, the initial reaction times for the choice, I could see sort of confidence signatures that were less movable, suggesting that even in the process of like pressing that button, there was some kind of change in the representation that was being made. I mean, that's a very loose description of what we did, but it was enough for me to be convinced that even that act of asking them to press the button had already, collapsed something or changed something so that the information was being processed in a different way, which kind of makes sense. Like once you've, carrying around information is expensive. So once you've made a decision and you're behaviorally moving on to the next thing, presumably it's reasonable to do something like that.
Yeah.
Eric, is this out?
No, long story, but it's sitting kind of it has some annoying, small annoying problems that either we have to spend a lot of time solving or it's going to go somewhere small. So if you're interested in talking to me about it, just send me a message. Maybe motivate me to try to push it out.
All right, so I realized that the poll was never ended, so I'll just end it now, and I guess I will show the results. I'm already forgetting
even more,
but I think maybe all of the 9 no's stayed, and that's why the proportion is a little higher. Yeah. Anyway.
I have a question for you, Dobie, actually, about your experiment. So has that actually changed or not?
I think it's very similar. It may have gone slightly down proportion-wise, but it may also be a bias sample. I also want to point out that, the people attending this may be a bias sample of the whole neuroscience community. So anyway.
In your experiment, did you guys ever try allowing them? So maybe I didn't quite understand the design completely. So I was a bit confused in that. Could you have allowed them to make multiple choices?
We could have, and we actually had one experiment like that I didn't show. The problem with multiple choices that I think I think what people are doing is they prepare 2 choices while viewing the stimulus. So the viewing duration is 500 milliseconds. It's sufficient that you take, you make 2 decisions in a row and just commit them to working memory. And I think for whatever reason, people don't do that in the other design that we have, which is just, give us one response, but we'll manipulate exactly what are the available options for you to make. But yeah, so when we did do that with two responses, the population model still overpredicted the accuracy, but the accuracy was way higher than the simple, straightforward summary model, which would just, you'd be a chance, so you're above chance. We had another variation of the summary model that was the best, but I don't know that I have like really high confidence in that summary model. But so it was, again, not very satisfying. Better than chance, so not the complete summary, but much less than what the population model would predict.
Yeah, I mean, I think Weiji's warning is well taken. That, I mean, the other thing that I guess I would say, I always worry about in these contexts is that, subjects bring lots of exogenous priors that are about like what actually the goal of the experiment was, and all these other things that make, trying to get these precise inferences out of behavior very tricky unless you really do a lot of forcing, which I guess is what he said by, really simulating out all of the possibilities.
No, I agree.
But anyway,
yeah. It is complicated. And I guess we came off as like, we're going to solve it, and people were like, no, you won't. But in a way, we're like, for me, it's like, even if we just present all of the difficulties, I think that's already useful, hopefully.
Yeah, I 100% agree. I mean, to me, a lot of the, I don't know, maybe I'm sorry, Ned's gone now, but I'm a little bit Wittgensteinian. I don't know whether he would appreciate that. But there's this idea that we have some of these problems that if we just actually clarify, the questions and the assumptions, then the problem will go away, or at least be transformed into a different problem. And I feel like your collaboration here is one where just really clarifying the playing field and like really laying out all of the different perspectives in the landscape and what the possible boundaries are and their implications is sort of enormously useful. Because I guess I read a lot of papers that seem to be slightly talking across each other, in that they seem to have slightly different definitions, and therefore they apparently disagree, where probably their interpretations that would be different if you so I think that would be a fantastic outcome minimally. And if you are able to produce an experimental result to push the weight of evidence one way or another, then even better. Anyway, I guess it's getting late for you guys, so thanks.
Awesome. Well, thank you, everybody. I think this is it. I think we'll just stop the recording now. Thank you all for attending. Those 10 of you who are still here. All right. Bye, everybody.
All right, bye.
Bye, Daryl. Bye, Eric.
That was fun.
Bye.
Bye.